Our universe teems with enigmas. From the smallest quantum particles to the largest cosmic structures, mysteries abound. Scientists have made remarkable strides in unraveling the cosmos, yet with each discovery, new questions emerge. Join us today as we embark on a journey through the uncharted territories of our extraordinary universe. Dark matter is one of the universe's most intriguing mysteries, comprising approximately 27% of the cosmos. It is an unseen substance that does not emit light or any form of electromagnetic radiation, making it virtually invisible to our current instruments. While we cannot directly observe dark matter, its existence is inferred from its gravitational influence on visible matter, radiation, and the structure of the universe itself. Galaxies rotate in such a way that they appear to contain far more mass than what we can detect through telescopes, suggesting that a significant amount of matter is present, yet hidden from our view. One of the primary reasons dark matter remains elusive is that it does not interact with electromagnetic forces, the very forces that allow us to see objects through light. Without electromagnetic interaction, dark matter cannot reflect or emit light, rendering it invisible. Scientists have theorized that dark matter particles may interact through other forces, such as gravitational forces, but the details remain unclear. This leads to fascinating speculation about what dark matter actually consists of, with proposals including exotic particles like weakly interacting massive particles or axions. Dark matter plays a crucial role in shaping the large-scale structure of the universe. It extends beyond galaxies, forming a vast cosmic web that influences galaxies' formation, movement, and clustering. Observational evidence, such as the cosmic microwave background radiation and galaxy cluster formation, supports the idea that dark matter acts as a scaffolding for normal matter to coalesce and form into the structures we observe today. Understanding dark matter is essential for a complete picture of the universe's composition and evolution. As scientists develop more sophisticated detectors and seek ways to create dark matter particles in laboratories, the quest to unveil this enigmatic substance continues, promising to deepen our understanding of what the universe truly is and how it operates. Detecting dark matter is a complex endeavor since it does not emit light and barely interacts with ordinary matter. Scientists rely on indirect methods to infer its presence, primarily through the gravitational effects it exerts on galaxies and galaxy clusters. By studying the rotation curves of galaxies, researchers have noted that the outer regions rotate faster than expected, based solely on visible matter. This discrepancy indicates that a substantial amount of unseen mass, attributed to dark matter, is influencing these rotations. Another method called gravitational lensing provides compelling evidence for dark matter's existence. When light from distant objects passes near massive clusters of galaxies, the gravity of the cluster bends the light, creating distorted images or multiple images of the same object. By analyzing these distortions, scientists can map out the distribution of mass in the lensing cluster. The amount of visible matter alone does not account for the observed lensing effects, reinforcing the idea that dark matter must be present to account for the additional gravitational pull. Additionally, scientists are exploring direct detection methods using highly sensitive detectors located underground to shield them from other background radiation. These detectors aim to catch rare interactions between dark matter particles and ordinary matter. Various experiments are ongoing, attempting to identify potential dark matter candidates like weakly interacting massive particles. Although no definitive detection has occurred yet, ongoing advancements in technology and methods continue to generate hope. Astrophysical observations also play a role in piecing together the dark matter puzzle. The cosmic microwave background radiation provides a snapshot of the early universe, allowing scientists to study the distribution of dark matter shortly after the Big Bang. This information helps refine models of structure formation and the role dark matter has played in developing the universe as we know it. Collectively, these methods form a multifaceted approach to unveiling the secrets of dark matter. Several compelling theories have emerged regarding the composition of dark matter, each attempting to explain its elusive nature. One of the leading candidates is weakly interacting massive particles, commonly referred to as WIMPs. These hypothetical particles are predicted to have mass and interact via weak nuclear forces, making them challenging to detect. The appeal of WIMPs lies in their ability to naturally arise from extensions of the standard model of particle physics, particularly in supersymmetric theories, which predict a stable, massive particle that could constitute dark matter. Another intriguing candidate is axions, which are extremely light particles theorized to be connected to the strong nuclear force. Initially proposed to solve a problem in quantum chromodynamics, axions may also account for dark matter. Their predicted properties allow for a vast abundance throughout the universe, potentially rendering them invisible to current detection methods. Experiments aimed at detecting axions are being developed, leveraging their potential interactions with photons in magnetic fields. Some theories suggest that dark matter may consist of primordial black holes formed in the early universe. These small black holes could serve as a dark matter candidate if they were created shortly after the Big Bang. Their existence would reconcile some of the observational characteristics associated with dark matter, but determining the abundance and properties of such black holes remains a challenge. Lastly, alternative theories propose modifications to gravity itself, notably through concepts such as modified Newtonian dynamics, or MOND. Rather than posit additional unseen matter, these theories seek to explain galactic behaviors through altered gravitational physics. While these models have gained traction in some research circles, they currently lack broad acceptance compared to particle physics-based explanations. Each of these theories, whether particle-based or gravity-modifying, highlights the ongoing quest to understand what dark matter truly is and how it influences the universe around us. Dark energy and dark matter are two distinct components of the universe, each playing a different role in its structure and behavior. Dark matter is primarily responsible for the gravitational attraction that holds galaxies together and influences their formation. It accounts for a significant mass that we cannot see but can infer through its gravitational effects on visible matter. In contrast, dark energy is a pervasive force thought to be driving the accelerated expansion of the universe. This mysterious energy makes up roughly 73% of the universe's total energy density, acting in opposition to the gravitational attraction exerted by matter. While dark matter clusters around galaxies and forms a framework for the structures we observe, dark energy exists uniformly throughout space. Its influence becomes more prominent on cosmological scales, affecting the growth of large-scale structures over time. Observations reveal that rather than slowing the expansion of the universe due to the gravitational pull of matter, dark energy accelerates it. This surprising phenomenon was first discovered in the late 20th century when astronomers observed supernovae that appeared dimmer than expected, suggesting that distant galaxies were moving away from us faster than previously thought. The difference in behavior between dark matter and dark energy can also be understood through their respective properties. Dark matter interacts gravitationally, allowing it to accumulate and form structures in the cosmos. Dark energy, on the other hand, is characterized by a negative pressure that counteracts the attractive force of gravity, leading to the expansion of space itself. This unique property of dark energy has profound implications for the fate of the universe, as it suggests a vast, increasingly empty future. As researchers continue to study both dark matter and dark energy, they realize that understanding these two components is crucial for sketching a complete picture of the cosmos. They may even be interconnected in ways we have yet to discover, leading to groundbreaking insights into the fundamental nature of the universe itself. The universe's expansion is accelerating due to the influence of dark energy, a mysterious force that constitutes a significant portion of the universe's total energy density. Observations made at the end of the 20th century, particularly those involving distant supernovae, revealed that rather than slowing down as previously expected, the universe's expansion is speeding up. This counterintuitive result prompted scientists to explore the idea of a repulsive force acting against gravity, which they named dark energy. Dark energy is believed to have a uniform presence throughout the cosmos, exerting a negative pressure that acts on the fabric of space itself. Unlike ordinary matter and dark matter, which clump together under gravity, dark energy resists this attraction, leading to the accelerated expansion we observe today. The exact nature of dark energy remains one of the most profound challenges in cosmology, as scientists continue to investigate whether it is a fundamental property of space, an unknown field, or perhaps a result of modifications to our understanding of gravity. One of the leading theories regarding dark energy is the cosmological constant, initially introduced by Albert Einstein in his equations of general relativity. This constant represents a fixed energy density that fills space uniformly. When incorporated into the equations of cosmology, it suggests that as the expansion of the universe increases, dark energy becomes more dominant, allowing for accelerated growth. Although this concept matches many observations, other theories postulate varying forms of dark energy, each with its own implications on the universe's fate. The implications of an accelerating universe are profound. It suggests that as time progresses, galaxies will move further away from one another, leading to a future characterized by cold, dark expanses of space with fewer visible stars and galaxies. Understanding dark energy is not only crucial for comprehending the dynamics of the universe, but also for contemplating its ultimate destiny. It remains a central focus of research in contemporary cosmology, as scientists strive to unlock the secrets behind this enigmatic force. If dark energy did not exist, the universe would likely have a very different future. Currently, dark energy is driving the accelerated expansion of the universe, meaning that galaxies are moving away from each other at an increasing rate. Without this mysterious force, the dynamics of cosmic expansion would change dramatically. Instead, the gravitational attraction of matter, both visible and dark, would dominate the behavior of the universe. In a scenario without dark energy, the expansion of the universe would gradually slow down due to the gravitational attractions between galaxies and other celestial bodies. This slowing effect could lead to various potential outcomes depending on the overall density of matter in the universe. If the density of matter was sufficiently high, gravitational forces could eventually overcome the expansion, potentially leading to a big crunch. In this scenario, the universe would stop expanding and begin to contract, ultimately collapsing back into a singular state. Conversely, if the density of matter were precisely at a certain critical limit, the universe could continue to expand forever, but at an ever-decreasing rate. This would represent a flat universe where the expansion would slow, but never fully stop. Without the repulsive influence of dark energy, such a universe would become less dynamic over time, leading to a future filled with dark, increasingly isolated galaxies. The existence of dark energy also provides an explanation for the current observations that indicate the universe is not only expanding, but doing so at an accelerating rate. Without dark energy, the observations of distant supernovae and the large-scale structure of the universe would lead to different interpretations of cosmic evolution. Ultimately, the absence of dark energy would reshape our understanding of cosmology and the fate of the universe, leading to a cosmos governed solely by gravitational interactions and the matter within it. Astronomers employ several sophisticated techniques to measure the effects of dark energy, each leveraging the vastness of the universe and the light it emits in different forms. One of the most significant methods involves observing distant supernovae, particularly type Ia supernovae. These stellar explosions exhibit consistent brightness, allowing astronomers to use them as standard candles for gauging cosmic distances. By measuring how dim or bright these supernovae appear from Earth, scientists can calculate their distance and track how fast they are moving away. The surprising result, that these supernovae appear dimmer than expected, indicates that the universe's expansion is accelerating, a phenomenon attributed to dark energy. Another powerful technique is gravitational lensing, which examines how light from distant galaxies is bent by massive objects, such as galaxy clusters in the foreground. The extent of this bending provides valuable information about the mass distribution of both visible and dark matter, allowing astronomers to infer the effects of dark energy on the overall structure of the universe. By studying how these gravitational lensing effects change with distance, researchers can gather insights into the nature of dark energy and its influence on the expansion rate of the cosmos. Cosmic microwave background radiation, the afterglow of the Big Bang, serves as another crucial tool in measuring dark energy. This faint radiation permeates the universe and encodes information about the early conditions of the cosmos. By analyzing temperature fluctuations and the distribution of these fluctuations across the sky, scientists can infer critical parameters related to dark energy, such as its density and constant effects. Measurements of the cosmic microwave background provide a cross-check against observations from supernova and large-scale structures. Lastly, the study of galaxy distributions and their clustering over time allows researchers to observe how structures evolve in the universe under the influence of dark energy. By mapping out how galaxies are spaced and how they group together, astronomers can detect patterns consistent with dark energy's effects on cosmic expansion. Combining all these methods helps create a comprehensive picture of dark energy, enhancing our understanding of its role in shaping the universe we observe today. While dark matter and dark energy are the leading explanations for various astronomical observations, several alternative theories seek to explain these phenomena. One prominent alternative for dark matter is the idea of modifying the laws of gravity, particularly through theories such as modified Newtonian dynamics, or MOND. MOND suggests that Newton's laws of motion break down at very low accelerations, which occurs in the outer regions of galaxies. This modification accounts for the observed rotational velocities of galaxies without requiring the presence of unseen mass. Although MOND can explain certain galaxy behavior, it struggles with large-scale structure formation and cosmological observations, making it a less favored option. Another proposal revolves around the existence of fifth forces or extra interactions that may impact the behavior of matter on cosmological scales. These theories hypothesize additional fundamental forces that could alter gravitational interactions, potentially explaining the rotation curves of galaxies without invoking dark matter. However, these models usually lack strong empirical support and have not been widely accepted in the scientific community. For dark energy, one alternative is the idea of an evolving or dynamic field known as quintessence. This theory posits that dark energy is not a simple cosmological constant, but rather a fluid-like field that can change over time and space. Quintessence could explain varying expansion rates and may link the effects of dark energy with the overall dynamics of the universe. Still, there are challenges in distinguishing this behavior from a static cosmological constant. Another hypothesis suggests that the effects attributed to dark energy could arise from inhomogeneities in the distribution of matter in the universe. This approach focuses on analyzing how structure affects observations of cosmic expansion, positing that the universe appears to accelerate simply due to the non-uniform distribution of galaxies and matter. While this concept offers fascinating insights, it also requires compelling evidence to support it against the robust framework that dark energy provides. These alternative explanations continue to stimulate scientific inquiry and debate within the field of cosmology. While dark matter and dark energy remain the prevailing theories, exploring these alternatives helps deepen our understanding of the universe and its underlying principles. Inside a black hole's event horizon, the laws of physics as we understand them begin to break down. The event horizon itself acts as a boundary beyond which no information or matter can escape the black hole's gravitational pull. Once anything crosses this threshold, it is irrevocably drawn toward the singularity, a point at which density becomes infinite and the structure of space-time is believed to collapse. As matter approaches the event horizon, it experiences extreme gravitational forces. This process can lead to the formation of a tidal effect, where the gravitational pull is significantly stronger on one part of an object than on the other. This disparity creates intense stretching and compressing, sometimes referred to as spaghettification, as objects are pulled apart. This phenomenon would be particularly severe for smaller black holes, while larger black holes would exhibit a more gradual increase in tidal forces. Once inside the event horizon, classical concepts of space and time begin to lose their meaning. According to general relativity, time itself behaves bizarrely near a black hole. An observer falling into a black hole would perceive time normally, but an outside observer would see the infalling object slow down and never quite seem to cross the event horizon. Thus, the experience of time differs dramatically depending on one's perspective. The singularity at the core of a black hole presents significant challenges to our current understanding of physics. At this point, where gravity is thought to be infinitely strong and space-time curves infinitely, classical physics breaks down and quantum effects become pronounced. As a result, physicists continue to grapple with reconciling the principles of general relativity with quantum mechanics, striving to develop a more comprehensive theory that can accurately describe what happens in these extreme environments. The mysteries of black holes invite continued exploration, pushing the boundaries of our understanding of the universe's fundamental nature. Supermassive black holes, which can contain millions to billions of times the mass of our Sun, are found at the centers of most galaxies, including our own Milky Way. Their formation is a complex process that likely involves several contributing factors with significant stages over cosmic time. One leading theory suggests that these massive black holes originate from the merging of smaller black holes and large clouds of gas in the early universe. Initially, when the universe was young, it was filled with vast regions of densely packed gas. As these gas clouds collapsed under their own gravity, they could have formed the first generation of stars. The most massive of these stars would eventually live short, explosive lives, ending in supernovae, which could result in the formation of stellar black holes. Over time, these stellar black holes might collide and merge with one another, forming larger black holes. Meanwhile, the accumulation of surrounding gas can play a crucial role in this process. As gas falls toward a developing black hole, it heats up and emits radiation, causing it to collapse more rapidly than it would otherwise. This accretion of gas and stars can create the conditions necessary for black holes to grow significantly. If conditions allow, this process can lead to the formation of a black hole that reaches supermassive masses more swiftly. Another avenue of formation involves the direct collapse of massive gas clouds. In this scenario, if a sufficiently dense gas cloud collapses under its own weight without forming stars, it can create a massive black hole directly. This may have occurred in the early universe, where dense regions facilitated rapid black hole growth. Over billions of years, these supermassive black holes can continue to grow by swallowing nearby stars and gas, as well as merging with others when galaxies collide. Such mergers are thought to be common in the universe's history, particularly during epochal cosmic events where galaxies interact and merge. The prevalence of supermassive black holes at galaxy centers is closely tied to this complex interplay of gravitational dynamics, stellar evolution, and cosmic evolution over time, resulting in the enormous black holes we observe today. Hawking radiation is a theoretical prediction made by physicist Stephen Hawking in 1974 that describes a process by which black holes can emit radiation and ultimately lose mass. According to quantum mechanics, pairs of virtual particles are constantly forming and annihilating in empty space. Near the event horizon of a black hole, one of these particles can fall into the black hole while the other escapes. If the escaping particle has positive energy, it can appear as radiation emitted by the black hole itself. This phenomenon leads to intriguing implications for black hole dynamics. As a black hole emits Hawking radiation, it gradually loses mass and energy, effectively shrinking over time. If the rate of radiation emission exceeds the rate of material falling into the black hole, it could lead to the eventual evaporation of the black hole entirely. This process may take extremely long periods, potentially billions of years for a large black hole. However, for smaller black holes, the effects of Hawking radiation would be more pronounced, leading to a faster rate of evaporation. The existence of Hawking radiation poses significant questions about the ultimate fate of black holes and their information. If a black hole evaporates completely, the conundrum arises regarding what happens to the information about the matter that fell into it. This has sparked much debate and research in theoretical physics, as it challenges our understanding of quantum mechanics and general relativity. The so-called information paradox highlights a fundamental conflict in current theories, prompting scientists to explore potential resolutions, such as holographic principles or other modifications to existing frameworks. While Hawking radiation has not yet been directly detected, it remains a cornerstone of theoretical discussions surrounding black holes. Its implications extend beyond black hole thermodynamics, impacting our overall comprehension of the universe's laws and the intricate relationship between gravity and quantum mechanics. As researchers continue to delve into the mysteries of black holes, the concepts surrounding Hawking radiation will play a crucial role in advancing our knowledge of fundamental physics. The question of whether information can escape from a black hole is one of the most profound and perplexing challenges in modern theoretical physics. It stems from the implications of Hawking radiation and the so-called information paradox that arises from combining the principles of quantum mechanics and general relativity. According to general relativity, once something crosses a black hole's event horizon, it is thought to be irretrievably lost. However, the concept of information preservation in quantum mechanics suggests that information cannot simply vanish. When Stephen Hawking proposed his theory of radiation emitted by black holes, he indicated that this radiation did not carry information about the matter that had fallen into the black hole. This leads to a contradiction. If a black hole can evaporate completely due to Hawking radiation, then what happens to the information contained within the objects and matter that crossed its event horizon? This apparent loss of information violates a fundamental tenet of quantum mechanics, which holds that information must be conserved. Various researchers have explored potential resolutions to this paradox. One prominent idea is that information may actually be encoded in the Hawking radiation itself, meaning that while it might not be immediately accessible, it could, in theory, be deciphered from the emitted radiation as the black hole evaporates. This idea leads to speculation about the possibility that the radiation contains subtle features that reflect the initial states of the matter that fell into the black hole. Another proposed resolution involves the holographic principle, which posits that all the information contained within a volume of space can be represented as a theory on the boundary of that volume. In this framework, the black hole's event horizon could store the information in a two-dimensional form, allowing it to be retrieved in some manner despite being inside the black hole. As researchers continue to investigate these ideas, the debate surrounding information escaping from a black hole remains ongoing. Although promising theories are emerging, no definitive resolution has yet been found. The interplay between black holes and the mysteries of information conservation may ultimately lead to groundbreaking insights into the fundamental laws of the universe. Primordial black holes are a unique class of black holes believed to have formed in the early universe, soon after the Big Bang. Unlike the stellar black holes that result from the collapse of massive stars, primordial black holes are hypothesized to have formed from fluctuations in density during the universe's rapid expansion. These fluctuations could have led to regions where matter was densely packed, causing gravitational collapse into black holes in a range of masses, from very small to potentially supermassive. One of the fascinating aspects of primordial black holes is that they could have formed in a variety of sizes. Some might be as small as an atom, while others could be as massive as the sun or even grander. Their existence could help explain several phenomena in cosmology, including dark matter. Since primordial black holes could account for some or all of the missing mass in the universe, researchers continue to explore their potential contributions to our understanding of cosmic evolution. The hunt for evidence of primordial black holes involves indirect methods, since they would not emit light in a detectable way. Instead, scientists look for their gravitational effects on surrounding matter. For instance, if primordial black holes are present in sufficient numbers, they could contribute to gravitational lensing effects or influence the orbits of stars in galaxies. Additionally, Certain theories suggest that they might lead to detectable signals such as gravitational waves if they collide or interact with other celestial bodies. As of now, the existence of primordial black holes has not been confirmed. However, they remain a topic of considerable theoretical interest and active research. Observations from gravitational wave detectors, cosmic microwave background studies, and analyses of galaxy formation could one day provide the concrete evidence needed to confirm whether these fascinating cosmic objects are part of our universe's complex fabric. Binary black hole systems evolve through a series of complex interactions that lead to their eventual merger. These systems consist of two black holes in a mutual gravitational orbit, and their evolution is influenced by several factors, including their initial separation, mass, and the environment around them. Initially, the two black holes can be formed from the remnants of massive stars in a binary star system, or they could originate from the gravitational collapse of dense regions in the early universe. As the black holes orbit each other, they gradually lose energy due to the emission of gravitational waves. According to the principles of general relativity, whenever massive objects like black holes accelerate, they create ripples in space-time known as gravitational waves. These waves carry energy away from the system, causing the black holes to spiral closer together over time. As they lose energy, the orbital period decreases and the black holes accelerate toward one another. When the black holes come very close, approaching the event horizon of each black hole, they undergo a complex process known as the final merger. This stage is marked by a rapid increase in the emission of gravitational waves, which can be detected by observatories like LIGO and Virgo. The merger happens extremely quickly on cosmic timescales, resulting in a single, larger black hole, which is typically less massive than the combined mass of the two original black holes. This mass difference is due to the release of energy in the form of gravitational waves during the merger. After the merger, the newly formed black hole might undergo a process called ringdown. In this phase, the black hole settles into a stable state, emitting gravitational waves as it vibrates and loses remaining irregularities from the merger. Eventually, it reaches a stable configuration, becoming a single, more massive black hole. The study of binary black hole systems and their mergers has opened up a new field of astrophysics, allowing scientists to probe fundamental aspects of gravity and space-time. The detection of gravitational waves from these events has provided direct evidence of black hole merging, offering a deeper understanding of the nature of black holes and their growth in the universe. When two galaxies that each host a supermassive black hole approach each other, a fascinating and complex series of events unfolds. Initially, the gravitational forces of each galaxy exert a powerful pull on the other. As the galaxies draw closer together, their stars, gas, and dust start to interact. This interaction can trigger rampant star formation, igniting new stars as gas clouds collapse under the immense pressures created by these encounters. As the galaxies merge, their supermassive black holes also migrate towards one another, drawn by their respective gravitational fields. Over time, these black holes can exchange energy with their surrounding stars and gas, gradually losing energy and spiraling inward. This phenomenon can lead to what is known as a binary black hole system, where the two supermassive black holes orbit each other closely. Eventually, these black holes may reach a point where they can no longer resist the pull of gravity. As they close in, they merge into a single, even more massive black hole, releasing immense amounts of energy in the process. This final merger generates gravitational waves, ripples in the fabric of space-time, detectable by observatories on Earth. These waves provide valuable information about the properties of the black holes and the dynamics of their merger. The aftermath of this colossal collision can reshape the galaxies involved. The new merged black hole will influence the orbits of stars and gas in the resulting galaxy, leading to further interactions and potentially new periods of star formation. The entire process exemplifies the intricate dance of gravity in the universe, showcasing how even the most massive structures can come together and dramatically transform. Quasars, or quasi-stellar objects, are among the brightest and most energetic phenomena in the universe, intimately tied to supermassive black holes. When a supermassive black hole is surrounded by a significant amount of gas and dust, it can create a massive accretion disk, where material spirals inwards due to the powerful gravitational pull. As this material accelerates and heats up, it emits an intense amount of energy, producing the luminosity characteristic of quasars. The energy emitted by a quasar can outshine entire galaxies, and this extraordinary brightness allows astronomers to observe them even at great distances. Quasars are often found in the early universe, giving us a glimpse into conditions billions of years ago. They serve as important cosmic beacons, helping scientists understand the growth and evolution of supermassive black holes and their host galaxies over cosmic time. Additionally, the behavior of quasars can vary dramatically. Some may be highly variable in brightness, indicating dynamic changes in the accretion processes around the black hole. Others might exhibit jets that extend far into space, launched by the magnetic fields and rotational forces surrounding the black hole. These jets can have a significant impact on their environments, influencing star formation rates in nearby galaxies and altering the intergalactic medium. Research into quasars not only aids in mapping the distribution of supermassive black holes across the universe, but also provides insights into the processes of galaxy formation and evolution. By studying these enigmatic objects, scientists unlock the secrets of how black holes grow and interact with their surroundings, offering a deeper understanding of the universe's history. The initial rapid inflation of the universe, often referred to as the inflationary epoch, is theorized to have occurred just after the Big Bang. This concept arose from observations suggesting that the universe appears remarkably homogeneous and isotropic, meaning it looks similar in all directions. To explain this uniformity, physicists proposed that in the very early moments of the universe, a fraction of a second after its birth, it underwent an extraordinarily rapid expansion. This inflationary period is thought to be driven by a field known as the inflaton field. During this brief but intense expansion, the energy stored in the inflaton field caused the fabric of space-time itself to stretch exponentially. This inflation caused the universe to grow by many orders of magnitude in a minuscule time frame, smoothing out any irregularities and leading to the large-scale structure we observe today. One of the key consequences of this inflationary phase is the generation of quantum fluctuations. These small variations in density would eventually become the seeds for all the galaxies, stars, and cosmic structures we see in the universe. As the universe continued to expand and cool, these fluctuations began to grow under the influence of gravity, forming the complex web of structures that populate the cosmos. Inflation not only helps explain the uniformity of the universe, but also provides a framework for understanding its ultimate fate. It raises profound questions about the nature of the universe's energy content and the dynamics of cosmic expansion. While many aspects of this theory are still being explored, it remains a central piece in the cosmological puzzle of our origins. The asymmetry between matter and antimatter in the observable universe presents one of the most intriguing puzzles in modern physics. According to fundamental theories, the Big Bang should have produced equal amounts of both matter and antimatter. However, observations reveal that the universe consists predominantly of matter, with very little antimatter detectable in our vicinity. One of the leading explanations for this imbalance is a phenomenon known as baryogenesis. This theoretical process suggests that certain conditions in the early universe favored the production of matter over antimatter. In simple terms, there may have been slight differences in the interactions between particles and their antiparticles, leading to a slight excess of baryons, which are particles like protons and neutrons that make up atomic nuclei. One possible mechanism related to this asymmetry is found in the violation of a principle called charge parity symmetry, or CP violation. This principle states that the laws of physics should be the same if particles are replaced with their antiparticles and their spatial coordinates are inverted. However, experimental results indicate that certain weak force interactions behave differently when involving particles compared to their antiparticles. This tiny difference might have contributed to the preferential creation of matter in the early universe. Another factor could be the role of high-energy processes that occurred during the Big Bang. As the universe cooled and expanded, any antimatter produced at the time could have annihilated with matter almost immediately, leaving just enough matter behind to form the stars, galaxies, and all visible structures we observe today. Studies continue to explore this matter-antimatter asymmetry, with experimental physics and observations providing essential insights into this profound question of our universe's nature. The nature of time in the cosmos is a complex and fascinating concept that has puzzled philosophers and scientists alike. Unlike the straightforward progression of time we experience in our daily lives, time in the universe is influenced by several factors, such as gravity and the fabric of spacetime itself. According to Einstein's theory of general relativity, time is not an absolute entity. Instead, it is intertwined with space, forming a four-dimensional continuum known as spacetime. One intriguing aspect of time is its relationship with gravity. In regions of strong gravitational fields, such as near a massive object like a black hole, time passes more slowly compared to areas with weaker gravitational influences. This effect, known as time dilation, has been confirmed through experiments involving atomic clocks at different altitudes. As a result, an observer near a massive object would age more slowly relative to someone far away. This revelation fundamentally alters our perception of time, demonstrating that it can stretch and contract depending on the surrounding conditions. Another layer to the nature of time is its directional flow, often referred to as the arrow of time. This concept relates to the second law of thermodynamics, which states that entropy or disorder tends to increase in an isolated system. The progression towards greater entropy gives time its forward direction, allowing us to experience events unfolding in a linear fashion. However, on a cosmic scale, some theories speculate that time may not have the same linear characteristics. For instance, in the context of certain cosmological models, the universe might undergo cycles of expansion and contraction, leading to questions about whether time itself has a beginning or an end. Ultimately, time remains one of the most profound mysteries of the cosmos. Scientific exploration continues to investigate its fundamental properties, revealing layers of complexity that challenge our intuitions. Whether through the durations of cosmic events or the peculiarities of theoretical physics, understanding the true nature of time can offer deeper insights into the universe's structure and the fundamental laws that govern it. The four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are the foundation of our modern understanding of physics. However, the question of whether there are undiscovered forces beyond these four is a tantalizing one that sparks the imagination of many scientists and researchers. Various theories and experimental investigations suggest the potential for additional forces. One prominent idea is rooted in theories attempting to unify the fundamental forces, particularly in the context of string theory and theories of quantum gravity. These frameworks propose that all forces and particles might be interconnected, indicating that additional forces could exist in certain conditions or at different energy scales that we have yet to probe. Moreover, recent research into dark matter and dark energy has prompted speculation about interactions that may involve undiscovered forces. Dark matter, which makes up a significant portion of the universe's total mass, remains elusive as it does not interact with electromagnetic forces. Understanding dark matter's properties could point toward new interactions or forces that differ from those we currently know. Similarly, dark energy, believed to be responsible for the accelerated expansion of the universe, remains poorly understood, fueling speculation about its origins and whether it could hint at new forces. In addition to theoretical pursuits, experimental physics continues to search for anomalies in our current understanding of forces. High-energy particle collisions, such as those conducted at the Large Hadron Collider, may reveal deviations from expected results, which could indicate the presence of new forces or particles that expand our fundamental framework. While we have not yet confirmed the existence of additional forces, the landscape of physics is always evolving. Ongoing research and exploration could one day uncover new fundamental forces, reshaping our understanding of the universe in profound and surprising ways. The ultimate fate of the universe is a captivating subject that involves various scenarios shaped by the laws of physics and the universe's existing conditions. Current cosmological models propose several potential outcomes based on factors such as dark energy, cosmic expansion, and the overall density of the universe. One of the leading scenarios is known as the Big Freeze. In this scenario, the universe continues to expand indefinitely due to the influence of dark energy, a mysterious force driving the acceleration of cosmic expansion. As galaxies move away from each other, they will eventually drift beyond the observable horizon, making it impossible for them to interact. With the universe expanding, stars will run out of fuel, leading to a gradual dimming of galaxies. Over immense timescales, black holes will be the last remnants of stellar objects, slowly evaporating through a process called Hawking radiation. Eventually, the universe will become an increasingly cold and dark place, filled with sparse remnants of matter and radiation. Another fascinating possibility is known as the Big Crunch. This scenario posits that if the density of matter in the universe is high enough, gravitational forces could ultimately halt the expansion and reverse it. Under this condition, the universe would begin to contract, leading to a collapse back into a singularity. This would create a situation where all matter and energy are compressed into an infinitely dense point, mirroring the conditions of the Big Bang. While current data suggest that this scenario is less likely given the observed acceleration of expansion, it remains a theoretical consideration. A more speculative idea involves the Big Rip. In this scenario, if dark energy's repulsive effects increase over time, they could eventually tear apart galaxies, stars, planets, and even atomic structures. In this outcome, all matter would be pulled apart, resulting in a universe that could end in complete disarray just before the fabric of space-time itself is disrupted. While researchers continue to explore these scenarios, the ultimate fate of the universe remains uncertain. Ongoing observations and theoretical work strive to refine our understanding, potentially revealing surprises about our universe's long-term future. Each possible outcome challenges our understanding of physics and elicits awe at the vastness and complexity of the cosmos. The heat death of the universe is a chilling concept that describes a state of maximum entropy, where the universe reaches a condition of uniform temperature and energy distribution. This scenario is predicated on the second law of thermodynamics, which states that entropy or disorder naturally increases over time in a closed system. As the universe evolves, processes such as star formation, nuclear fusion, and the eventual cooling of celestial bodies all contribute to increasing entropy. Initially, the universe will continue to expand, driven by dark energy, and stars will burn their nuclear fuel. Over trillions of years, star systems will age and eventually exhaust their fuel, leading to their transformation into red dwarfs, neutron stars, or black holes. As stars die, the energy they emitted will gradually dissipate into space. New stars may form from leftover gas and dust, but this process will become increasingly rare as the available material becomes depleted. With the passing of enormous amounts of time, even black holes will eventually evaporate through Hawking radiation. This quantum process, predicted by physicist Stephen Hawking, describes how black holes can emit radiation and lose mass over incredibly long timescales. The universe will gradually become populated with weakly interacting particles, radiation, and remnants of dead stars, creating a dark and cold environment. As the universe continues to cool, reaching temperatures close to absolute zero, all available energy will become evenly distributed. There will be no thermal gradients to facilitate work or energy transfer, leading to a state where no thermodynamic processes can occur. Matter and energy will be spread thinly across an unimaginably vast cosmos, resulting in a lifeless, stagnant universe, thus epitomizing the heat death scenario. The overall picture is one of stillness, where complexity diminishes, and any order that once existed is lost in an eternal expanse of uniformity. While this fate is trillions of years away, it showcases the eventual decline of cosmic dynamics, underscoring the intricate relationship between time and entropy in the universe. The question of what came before the Big Bang is one of the most profound inquiries in cosmology and physics. The Big Bang theory describes the birth of our universe as a rapid expansion from an initial singularity, a point of infinite density and temperature. However, because general relativity breaks down at this singularity, our current understanding struggles to describe conditions preceding it. Various hypotheses have been proposed to explore what might have existed before the Big Bang. One idea is the concept of a multiverse, suggesting that our universe is just one of many, possibly infinite universes, each with different physical laws and constants. In this framework, the Big Bang could represent a transition point in the life cycle of one universe among many, arising from the collapse or interaction of other structures in a broader cosmic landscape. Another intriguing possibility comes from certain theories in cosmology, such as the cyclic model. This model posits that the universe undergoes an infinite series of expansions and contractions. In this scenario, before our current universe began, there may have been a previous universe that collapsed upon itself in a big crunch, leading to another explosion and eventual expansion into what we now observe. Each cycle would erase the specifics of the previous universe while preserving some physical laws. There are also quantum gravity theories suggesting that time as we understand it may not have existed before the Big Bang, rendering the question of before somewhat meaningless. For instance, according to some interpretations of loop quantum gravity, the universe could have experienced a bounce rather than an explosion from a singularity, indicating that a different phase existed below our current understanding of time and space. The exploration of what preceded the Big Bang remains speculative, calling for deeper theoretical work and observational evidence to fully understand the universe's origins. As scientists investigate these profound questions, they delve into the fundamental nature of reality, time, and existence, hinting at mysteries that may reshape our comprehension of the cosmos. The seemingly perfect conditions of the universe that allow for the existence of life have led to the concept of fine-tuning. This idea suggests that various physical constants and laws are precisely set within a narrow range that permits the formation of stars, galaxies, planets, and ultimately, living organisms. Several factors contribute to this remarkable arrangement, sparking both scientific inquiry and philosophical debate. A prime example of this fine-tuning can be found in fundamental constants, such as the strength of gravity, the electromagnetic force, and the weak and strong nuclear forces. Each of these constants plays a crucial role in determining the structure and behavior of matter. For instance, if the strength of gravity was slightly weaker, galaxies, stars, and planets might not form. Conversely, if it was stronger, stars could burn out too quickly, leaving no time for life to develop. Such delicate balances suggest that the conditions for life depend on a specific set of parameters that exist only due to a remarkable coincidence. Several explanations aim to address this fine-tuning. One possibility is the anthropic principle, which posits that we can observe and question our universe's characteristics because we exist within it. In this view, the universe must accommodate observers like us, leading to the conditions we observe. However, this principle does not necessarily explain why those conditions exist in the first place. Another intriguing perspective involves the multiverse theory, suggesting that our universe is just one of many with varying constants and laws. If a vast number of universes exist, each with different properties, it is not surprising that at least one would possess the right conditions for life. In this scenario, we find ourselves in a universe suited for life simply because it is one of the lucky few that fit those criteria. The fine-tuning of the universe raises essential questions about the nature of existence and the underlying principles that govern our reality. As research continues into the cosmos's fundamental laws, our understanding of why the universe appears so perfectly calibrated for life remains both a scientific pursuit and a source of profound wonder. While astronomers have discovered thousands of exoplanets using various detection methods, many types remain elusive due to the limitations of our current technology. One significant category of undetected exoplanets includes those that are smaller and less massive than Earth. Techniques like the transit method and radial velocity measurement are often biased toward larger planets, as their gravitational effects and the resulting signals are easier to detect. As a result, exoplanets that are comparable in size or mass to our planet may be rare in the current datasets. Another class of exoplanets that has yet to be conclusively identified is the true Earth-like exoplanet situated in the habitable zone, often referred to as the Goldilocks zone. While we have found candidates that could be rocky and temperate, many of these planets are still waiting for detailed observations to confirm their atmospheric compositions and surface conditions. Transiting Earth-sized exoplanets in habitable zones are not frequently detected simply due to the alignment required for transits and the vast distances between us and potential candidates. Additionally, there are exoplanets that belong to more exotic categories, such as rogue planets, which are free-floating planets that do not orbit any star. These mysterious planets can be challenging to detect because they lack a host star's light, making them faint and hard to observe. Moreover, certain types of gas giants, like those that could exist in very narrow orbits close to their stars, might be difficult to identify as well due to their challenging detection signatures. Lastly, the presence of exoplanetary systems that exist in dense star clusters is still relatively unexplored. The gravitational interactions in such environments may lead to high rates of planet ejection, making traditional detection methods less effective. As observational technology improves and new methods are developed, we will likely uncover a broader variety of exoplanets, deepening our understanding of planetary systems beyond our own and potentially revealing environments where life may arise. The quest to understand how common Earth-like planets in the habitable zone of their stars is an exciting area of research in exoplanet science. Recent studies, particularly those from NASA's Kepler mission, have provided valuable insights into the abundance of such planets. The habitable zone is defined as the region around a star where conditions may be just right for liquid water to exist on a planet's surface, making it a key factor for potential habitability. Current estimates suggest that many stars in our galaxy could host Earth-sized or rocky planets in their habitable zones. Studies indicate that about 1 in 4 stars may have at least one planet within this region, and with billions of stars in the Milky Way, this could translate to hundreds of millions of potentially habitable planets. However, these estimates can vary based on the criteria used to define Earth-like and the specific characteristics considered necessary for habitability. While the presence of planets in the habitable zone suggests potential for life, not all such planets will necessarily be Earth-like in the conditions they provide. Factors such as the planet's atmosphere, geological activity, and the star's radiation environment play vital roles in determining habitability. For instance, a planet may be positioned within the habitable zone, yet still possess a thick, toxic atmosphere that precludes life as we understand it. As observational technology progresses, especially with upcoming missions like the James Webb Space Telescope, our ability to examine the atmospheres and conditions of these exoplanets will improve. Future research will help refine our understanding of how common Earth-like planets truly are and whether any exhibit conditions conducive to life. The search for such worlds continues to capture the imagination of scientists, promising exciting discoveries that may one day answer the age-old question of whether we are alone in the universe. Extreme exoplanets challenge our understanding of planetary systems and push the boundaries of what we consider possible in the universe. One such extreme example is WASP-17b, a hot Jupiter located about 400 light-years away. This gas giant is noteworthy for its incredibly close orbit around its host star, completing a full revolution in just under 1 day. The intense heat from its proximity to the star causes the planet to reach scorching temperatures, creating a dramatic atmospheric environment where gases may be vaporized. Another extreme exoplanet is HD 1088b, known as a lava planet. This planet is thought to be so close to its star that its surface is predominantly molten rock due to extreme temperatures. The composition and conditions suggest a landscape of flowing lava rivers, making it a hostile environment unfit for life as we know it. These conditions provide a stark contrast to Earth and present a fascinating opportunity to study planetary formation and evolution. An additional fascinating example is PHL 2483b, a planet with an atmosphere predominantly composed of gaseous titanium oxide, which contributes to a stark temperature gradient. Temperatures can soar excessively high, leading to various unique weather patterns. This extreme weather, alongside the planet's unusual chemical composition, makes it a captivating subject of study for planetary scientists. Lastly, there is TOI 2071b, an example of an exotic super-Earth. This planet exhibits characteristics unlike those found within our solar system, such as substantial atmospheric pressure and potential volcanic activity. Super-Earths like this may have unique geologies and atmospheres, revealing a wide diversity of environments that could exist in the cosmos. These extreme exoplanets not only highlight the incredible diversity of planetary types beyond our own solar system, but also provide valuable insights into the nature of planetary systems, their formation, and the complex processes that lead to their current states. As we continue to explore these worlds, they expand our understanding of what is possible throughout the universe. Searching for biosignatures on exoplanets involves a multifaceted approach that combines advanced observational techniques, innovative technology, and theoretical modeling. Biosignatures are indicators of biological activity, and our ability to detect them hinges on understanding the atmospheres and surface conditions of distant planets. Several methodologies are employed to identify potential biosignatures that might suggest the presence of life. One of the primary techniques for searching for biosignatures is through spectroscopy, which entails analyzing the light spectra emitted or absorbed by an exoplanet's atmosphere. When a planet transits or passes in front of its host star, some of the starlight filters through the planet's atmosphere. This light is altered by the gases present, and specific spectral signatures can reveal the presence of molecules associated with life, such as oxygen, methane, carbon dioxide, and water vapor. Detecting a combination of these gases in specific ratios could imply biological processes, especially if they are in disequilibrium, indicating ongoing production and consumption. Another approach focuses on direct imaging, which allows astronomers to capture the light from exoplanets themselves rather than just relying on the light from their stars. Advanced telescopes with sophisticated coronagraphs or star shades can block the overwhelming light of stars, enabling the observation of planets. This method can provide detailed information about the planet's atmosphere and surface conditions, revealing potential biosignatures. Furthermore, missions planned for the future, such as the James Webb Space Telescope, are expected to enhance our ability to detect biosignatures considerably. These missions will utilize infrared capabilities that can explore the atmospheres of Earth-like planets in greater detail. By examining the chemical compositions and temperature profiles of target exoplanets, scientists hope to identify patterns that indicate biological activity. The search for biosignatures also relies on theoretical modeling and simulations, which help scientists understand what types of biosignatures might be produced under diverse environmental conditions. This knowledge is crucial for both interpreting observational data and guiding future searches, ensuring that our methods remain aligned with the complexities of potential alien ecosystems. As technology advances and our understanding of exoplanetary systems deepens, the search for signs of life beyond Earth continues to be a thrilling endeavor in modern astronomy. Detecting microbial life on other worlds presents a host of significant challenges that stem from both the vastness of space and the limitations of current technology. One of the foremost difficulties is the sheer distance involved. Many potentially habitable exoplanets are located light years away, making direct observation complex and requiring highly sensitive instruments. Even for closer targets like Mars or the icy moons of Jupiter and Saturn, the remoteness complicates the collection and analysis of samples. Another major obstacle lies in the diverse environments where microbial life might exist. Extremophiles on Earth can thrive in harsh conditions such as deep-sea hydrothermal vents, polar ice, and acidic hot springs, suggesting that life could adapt to extreme environments elsewhere. However, without knowing the specific conditions of alien worlds and the types of life they might harbor, it becomes challenging to design effective instruments and experiments to search for life. This uncertainty complicates the definition of what biosignatures we should look for. Moreover, the validation of any potential biosignatures is inherently intricate. For example, certain gases like methane and oxygen can be produced both biologically and through abiotic processes. Distinguishing between these pathways requires careful analysis and context. For a biosignature to be considered reliable, it must not only be detected but also clearly attributed to biological activity, which is a complex endeavor in itself. Lastly, there is the challenge of sample collection and the need for in situ testing. Missions aimed at investigating microbial life, such as the Mars rovers, face logistical hurdles in obtaining samples from beneath the surface or from subsurface oceans on moons like Europa and Enceladus. Ensuring that instruments are equipped to analyze potential life forms while avoiding contamination from Earth-borne microbes adds an additional layer of complexity. These challenges illustrate the breadth of difficulties researchers face in the quest to detect microbial life beyond our planet. As technology advances and our exploration of the solar system and beyond continues, these obstacles may eventually be overcome, bringing us closer to answering the profound question of whether we are alone in the universe. Alien life could present a fascinating array of differences from life as we understand it on Earth. Firstly, the fundamental biochemistry of extraterrestrial organisms might vary significantly. While all known life relies on carbon-based molecules, alien life might utilize different elements entirely, such as silicon or even entirely new combinations of elements. This shift could lead to organisms with entirely different forms, structures, and functionalities. Environmental conditions play a crucial role in shaping life. On Earth, life thrives in a narrow range of temperatures and pressures, but alien life could exist in extreme environments. Imagine organisms that evolve on planets with high radiation, low temperatures, or even in environments rich in methane or ammonia. Their adaptations might include protective outer shells, unique metabolic processes, or ways to utilize the local chemical resources for energy, making their appearance and behavior vastly different from anything we know. The modes of reproduction and communication among alien species could also diverge from terrestrial norms. While many Earth organisms rely on DNA to pass genetic information, extraterrestrial life forms might have entirely different reproductive strategies. They could employ methods that do not involve cellular division or even a form of communication that is not based on sound or light. Instead, they might use chemical signals or electromagnetic fields to interact with one another, altering our understanding of social structures and ecosystems. Exploring these possibilities not only broadens our perspective on the diversity of life, but also encourages us to consider the vast expanse of the universe. As we research exoplanets and the conditions that might support life beyond Earth, we discover the potential for unique ecosystems and life forms that challenge our conventional views on biology. The search for extraterrestrial life ultimately raises essential questions about adaptability and the infinite ways life might manifest in the universe. Several intriguing locations within our solar system have captured the attention of scientists searching for signs of life. One of the most exciting candidates is Europa, a moon of Jupiter. Beneath its thick ice crust, Europa likely harbors a vast ocean of liquid water, kept warm by heat generated from gravitational interactions with Jupiter. This subsurface ocean creates an environment where microbial life might exist, potentially supported by chemical nutrients from the moon's rocky seafloor, much like extremophiles found in Earth's deep oceans. Another fascinating site is Enceladus, one of Saturn's smaller moons. Enceladus has geysers that spew water vapor and organic compounds into space, hinting at a subsurface ocean beneath its icy surface. The presence of these plumes, along with the molecules detected in them, makes Enceladus an excellent place to investigate for signs of life. The ocean's interaction with the Moon's rocky core could also create the conditions necessary for life to flourish. Mars remains a focal point in the search for extraterrestrial life within our solar system. Evidence suggests that liquid water once flowed abundantly on the surface, and there are places where subsurface water may still exist today. Recent findings of seasonal recurring slope lineae, which could indicate briny water activity, have rejuvenated interest in the potential for microbial life on the red planet. Ongoing missions aim to explore Martian soil and ice samples for biosignatures, which would provide critical insights into past or present life. Lastly, Titan, Saturn's largest moon, presents a rather distinct possibility due to its dense atmosphere and lakes of liquid methane and ethane. Although its surface conditions are radically different from Earth, Titan's chemical complexity and potential subsurface ocean might harbor unique forms of life that are entirely alien to our understanding. This diversification of habitats across our solar system emphasizes the importance of continued exploration and study, as each location offers its own unique possibilities for discovering life beyond Earth. Distinguishing between natural phenomena and potential technosignatures requires a combination of observational techniques, theoretical frameworks, and careful analysis of data. Scientists first rely on a well-established set of criteria to identify signs of technology in the universe. A technosignature is defined as a signal or structure that suggests the presence of intelligent life. This could include unusual emissions of electromagnetic radiation, structured light patterns, or artifacts in space that appear to be engineered constructs rather than natural formations. One of the primary methods involves utilizing spectroscopic observations to analyze the light emitted or absorbed by celestial bodies. Natural phenomena typically have a predictable spectrum based on known atomic and molecular processes. If an observed spectrum contains unusual patterns or specific frequencies that do not correspond to known natural sources, it might indicate a technosignature. For example, a regular and consistent signal that deviates from the expected noise could suggest technological activity, such as radio transmissions. Furthermore, scientists employ machine learning algorithms and statistical analysis to sift through vast amounts of astronomical data. These advanced computational techniques can identify anomalies that stand out from the typical background noise of natural signals. By comparing these anomalies against a database of known cosmic phenomena, researchers can filter out mundane events, honing in on those that could indicate extraterrestrial technology. Additionally, the context in which a signal is detected plays a crucial role. For instance, if a strong signal is received from a region of space where no natural sources have been identified, this could increase the likelihood that it is a technosignature. Collaborations between astronomers, astrophysicists, and other scientists are central to this investigation, enabling the development of sophisticated models to differentiate between the myriad natural processes in the universe and potential indicators of intelligent life. This ongoing search illustrates humanity's deep curiosity about our place in the cosmos and the thrilling possibility of encountering other civilizations. Cosmic voids are vast, empty regions of space that contain significantly fewer galaxies compared to typical areas of the universe. These expanses can stretch across tens to hundreds of millions of light years and can take on irregular shapes. Notably, they represent a prominent feature of the large-scale structure of the cosmos, where galaxies form interconnected filaments and clusters much like a cosmic web. The emptiness of these voids can be starkly apparent when compared to the agitation of galaxy-rich regions surrounding them. The formation of cosmic voids is believed to be deeply intertwined with the universe's evolution and the dynamics of gravity. Initially, in the early universe, matter was not uniformly distributed. Small fluctuations in density emerged, leading to the gravitational attraction of matter, which clumped together to form what would eventually become galaxies and clusters. As galaxies drew closer and created these denser regions, the surrounding areas experienced less gravitational attraction, causing matter to be drawn away. Over time, this phenomenon led to the creation of expansive voids where fewer galaxies reside. As the universe continued to expand, these voids grew larger, shaping the distribution of matter across the cosmos. The interplay between dark matter and baryonic matter played a significant role in this process. While dark matter forms the scaffolding of the cosmic web, baryonic matter, which makes up stars and galaxies, tends to accumulate in denser regions. This separation further deepens the gaps seen in cosmic voids, leading to a clear distinction between densely populated areas and their stark, empty counterparts. Understanding cosmic voids provides valuable insights into the fundamental properties of the universe, including the influence of dark energy and the gravitational forces at play. They are not mere emptiness. Rather, these voids reveal the intricate dance of cosmic forces that shaped the universe into the complex structure we observe today. Exploring these emptier expanses helps astronomers and physicists piece together the broader narrative of our universe's formation and evolution. Galaxy filaments and walls are critical components of the large-scale structure of the universe, forming a complex three-dimensional web that outlines the distribution of galaxies and dark matter. This cosmic web is characterized by vast, elongated structures known as filaments, which stretch across hundreds of millions of light years and connect clusters and superclusters of galaxies. At the same time, the empty regions in between these filaments are referred to as voids, contributing to the intricate pattern that defines the universe. The organization of these structures is heavily influenced by the gravitational forces inherent in the cosmos. In the early universe, matter was distributed unevenly due to quantum fluctuations during the inflationary period. These irregularities led to areas with slightly higher density, which, over billions of years, attracted more matter through gravitational pull. As gas and dark matter congregated, they formed the denser regions known as galaxy clusters at the intersections of filaments. This process is often described by the gravitational collapse of matter within an expanding universe, leading to a hierarchical structure where large structures form first and then give rise to smaller ones. Galaxy walls or sheets form as a consequence of the anisotropic distribution of matter in these filaments. These walls are thin slices of space that contain a significant number of galaxies and are typically found surrounding the denser regions of filaments. The interactions among galaxies within these walls can lead to the formation of new structures, such as galaxy groups and clusters, which further influence the arrangement of the cosmic web. Observations from large-scale surveys such as the Sloan Digital Sky Survey highlight the continuity of filaments and walls and their relationship with dark matter. Computer simulations further illustrate how these structures evolve over time, predicting that the universe will continue to expand and filaments will grow more pronounced as galaxies move toward them due to gravitational attraction. Understanding the organization of these cosmic structures not only sheds light on the past and present arrangement of matter in the universe, but also provides insights into the future evolution of our cosmos. The rotation of galaxies is primarily driven by the gravitational interactions between the mass within them, including both visible matter like stars and gas, as well as the largely invisible dark matter. When galaxies form, the gravitational pull of this accumulating mass causes the surrounding material to collapse into a rotating disk structure. This rotation is a manifestation of the conservation of angular momentum, a principle that states that an object in motion will maintain its angular velocity unless acted upon by an external force. As gas and dust come together to form stars, they tend to spiral inward while simultaneously rotating around the center of the galaxy. This process results in the flattened disk shape of spiral galaxies, where stars in the outer regions often rotate at high speeds. The rotation is not uniform, rather, different parts of the galaxy can rotate at different speeds, influenced by the distribution of mass within the galaxy. The gravitational pull ensures that stars further from the galactic center do not just drift away, but maintain their orbits around the galactic core. An important aspect of galactic rotation relates to the presence of dark matter. Observations have shown that the outer regions of galaxies rotate much faster than expected based on the visible mass alone. This discrepancy indicates that there must be additional unseen mass contributing to the gravitational field. Dark matter, which does not emit light and cannot be directly observed, is thought to exist in a halo around galaxies. This halo extends well beyond the visible structures of galaxies and significantly affects their rotation curves, leading to the discovery of dark matter as a crucial component in understanding galaxy dynamics. The rotation of galaxies also plays a role in their long-term evolution. As galaxies interact with one another through collisions or mergers, their rotational dynamics can change, causing new structures to form and existing ones to be altered. Studying galaxy rotation helps astronomers gain insight into the distribution of mass, the presence of dark matter, and the complex gravitational interplay that shapes the evolution of galaxies throughout the history of the universe. Galaxies undergo a remarkable evolution throughout cosmic history, shaped by a variety of processes including gravitational interactions, star formation, and the influence of dark matter. Initially, shortly after the Big Bang, small fluctuations in density led to the formation of the first structures in the universe. These early galaxies were relatively small and composed mostly of gas. Over time, gravitational forces caused these gas clouds to collapse, forming stars, which lit up the universe and initiated the process of galaxy evolution. As galaxies continued to form and evolve, they underwent a phase of rapid star formation, often referred to as the cosmic noon. During this period, roughly a few billion years after the Big Bang, galaxies were more active, allowing them to create massive numbers of stars. However, this exuberant star formation was eventually curtailed as the gas and dust necessary for star creation were depleted. The rate of star formation in these galaxies subsequently slowed down, marking a transition from an active to a more passive evolutionary stage. Gravitational interactions between galaxies also play a significant role in their evolution. Galaxies can collide and merge, which leads to dramatic changes in their structure and star formation activities. These mergers can trigger new bursts of star formation and lead to the formation of larger galaxies. The result of such interactions can be a diverse range of galaxy shapes and sizes, including elliptical galaxies that form from merging spiral galaxies. The influence of dark matter further complicates this evolutionary narrative, as it acts as the underlying framework that governs the gravitational behavior of these cosmic structures. In the more recent past, the dynamics of galaxy evolution have been profoundly influenced by environmental factors. Galaxies within dense clusters can experience interactions that strip away their gas, further slowing their star formation rates. This process contrasts with galaxies located in isolated regions of the universe, where they might evolve more slowly, maintaining their gas and star formation for longer periods. Today, many galaxies have settled into a state dominated by older stars, having transitioned from their tumultuous youth to a more quiescent phase, yet their evolutionary journey continues as they interact with their surroundings in an ever-evolving cosmic landscape. Magnetic fields play a vital yet often underappreciated role in shaping the universe's cosmic structures, influencing everything from galaxy formation to the behavior of interstellar gas and dust. These magnetic fields are present at various scales, from the tiny regions within stars to the vast stretches of intergalactic space. They arise predominantly from the motion of charged particles, such as electrons, within conductive materials like plasma. This process, known as dynamo action, enables the generation of magnetic fields, which subsequently interact with the matter in their vicinity, affecting how that matter behaves. One significant aspect of magnetic fields is their ability to influence the dynamics of gas clouds in the early universe, which are essential for star formation. As these clouds collapse under their own gravity, magnetic fields can exert pressure that counters gravitational forces. This interplay can regulate the rate of star formation by suppressing the collapse of gas in certain regions while allowing it to proceed in others. Additionally, magnetic fields can help channel the angular momentum of collapsing gas, contributing to the formation of rotating protoplanetary disks around young stars. In galaxy clusters, magnetic fields contribute to the formation and structure of the hot plasma that fills the space between galaxies, known as the intra-cluster medium. Observations of the synchrotron radiation emitted by relativistic electrons spiraling around magnetic field lines have revealed the presence of significant magnetic fields in these environments. These fields play a crucial role in heating the intra-cluster medium and influencing the behavior of cosmic rays, which can in turn affect galaxy evolution and the large-scale structure of the universe. Furthermore, magnetic fields interact with cosmic structures at larger scales, affecting the motion of galaxies along cosmic filaments. When galaxies interact within these regions, magnetic fields can influence their rotational dynamics and gas supply, mediating star formation processes. As a result, the presence of magnetic fields is a fundamental component of the mechanics that govern the growth and evolution of galaxies and clusters, illustrating how interconnected the various physical forces are in shaping the cosmos. This intricate relationship between magnetism and cosmic structures highlights the complexity of the universe and the various forces at play in its continued evolution. Galaxy clusters interact through a variety of fascinating mechanisms that dramatically influence their evolution and the overall structure of the universe. These interactions primarily occur due to gravitational forces, as clusters, which are massive concentrations of galaxies and dark matter, exert substantial gravitational pull on one another. When clusters come close, their mutual attraction can lead to phenomena such as gravitational merging, where two or more clusters combine to form a larger system. During these mergers, complex processes unfold. As clusters collide, the galaxies within them can pass through one another relatively unhindered due to the vast distances between them. However, the hot gas that fills these clusters, known as the intra-cluster medium, becomes highly dynamic. The collision of this gas can produce shocks and triggers significant heating, which can elevate the temperatures of the gas dramatically. This results in increased X-ray emissions, allowing astronomers to study the interactions through high-energy observations. The effects of these interactions extend beyond mere merging. They can also lead to the formation of large-scale structures in the universe. When clusters collide, they can strip gas from one another and redistribute it. This can influence star formation rates within the galaxies as gas reservoirs are altered. Mergers and interactions can create spectacular events, such as the formation of new galaxies or the triggering of intense bursts of star formation, changing the dynamics of the participating clusters. In addition to merging, clusters can interact through gravitational lensing, a phenomenon that occurs when the mass of one cluster bends the light from more distant galaxies. This effect not only helps in mapping dark matter distributions within and around clusters, but also allows astronomers to study the characteristics of galaxies located beyond the foreground cluster. Such interactions highlight the interconnected fabric of the cosmos, illustrating how galaxy clusters function as both individual entities and part of an extensive, intricate cosmic web. Each interaction has lasting consequences on the clusters involved, helping to shape the evolution of galaxies and the large-scale structure of the universe itself. Intergalactic gas and dust are essential components of the cosmos, filling the vast spaces between galaxies and playing a crucial role in the evolution of the universe. This material, often termed the intergalactic medium, primarily comprises low-density hydrogen and helium, along with trace amounts of heavier elements and compounds. The intergalactic gas is crucial for feeding galaxies and aiding in the processes of star formation, while dust particles, though less abundant, contribute to the thermal and chemical dynamics of the universe. The intergalactic gas exists in different phases, including warm, hot, and cold varieties, depending on its temperature and density. The hot phase, consisting mainly of ionized hydrogen, can reach temperatures of several million degrees Celsius. This gas is found in regions like the filaments of the cosmic web, where it serves as a medium for the flow of material between galaxies. Meanwhile, the cold phase, which contains neutral hydrogen and molecules, tends to clump together and can eventually collapse to form new stars. Dust, on the other hand, is composed of tiny solid particles, including elements like carbon, silicon, and iron, typically produced in the late stages of stellar evolution or during supernova explosions. Although intergalactic dust is much less abundant than gas, it plays a critical role in various processes. For instance, it can absorb and scatter light, affecting our observations of distant galaxies. This dust also facilitates the formation of molecular hydrogen, a building block for new stars and planets, by providing surfaces on which chemical reactions can occur. Interactions between intergalactic gas and dust with galaxies are fundamental to understanding the life cycle of cosmic matter. This material can be drawn into galaxies during their formation and evolution, fueling ongoing star formation and contributing to the growth of galaxies over time. The study of this elusive intergalactic medium helps astronomers piece together the intricate connections between galaxies and the larger structures that shape our universe, showcasing the dynamic nature of cosmic evolution. Superclusters of galaxies are among the largest structures in the universe, formed through the complex interplay of gravitational forces and the dynamics of cosmic expansion. These vast groupings can contain dozens of galaxy clusters and groups spanning millions of light-years. The formation of superclusters begins in the early universe when tiny fluctuations in density emerged shortly after the Big Bang. These small variations led to the accumulation of matter, primarily through gravitational attraction, which favored regions of higher density. As matter clumped together under its own gravity, the early universe's gas and dark matter began to form individual galaxies and their clusters. Over time, these clusters, like the fundamental building blocks of superclusters, would drift closer together as the universe continued to expand. The mutual gravitational pull among nearby clusters leads to the merging of smaller structures into larger ones, gradually assembling superclusters over billions of years. The evolution of superclusters is also influenced by the surrounding cosmic web, which consists of filaments and voids. These filaments, composed of dark matter and gas, guide the motion of galaxies and clusters as they fall toward denser regions due to gravitational attraction. This process results in a dynamic environment where superclusters can form and evolve continually through interactions with other clusters. As clusters collide, they not only merge but can also experience significant transformations, such as the redistribution of gas, triggering bursts of star formation and altering the galaxies within them. Over time, superclusters exhibit various structural characteristics, including complexity and diversity in galaxy types. Their evolution is not static, instead it is shaped by ongoing gravitational interactions, mergers, and even the influence of dark energy, which drives the accelerated expansion of the universe. The study of superclusters provides valuable insights into the overall structure and evolution of the cosmos, revealing the intricate connections between galaxies and the vast scales of cosmic architecture that define our universe. Quantum entanglement is one of the most fascinating aspects of quantum mechanics, involving a unique connection between particles that allows them to share information instantaneously, regardless of the distance separating them. When two particles become entangled, their quantum states become intertwined, meaning that the state of one particle is directly correlated with the state of the other. This relationship holds true no matter how far apart the particles are, leading to the peculiar situation where measuring one particle immediately affects the other. This phenomenon does not involve the transmission of information in the classical sense. Rather, it reflects the non-local nature of quantum mechanics. When entangled particles are separated by vast distances, the measurement of one particle's state seems to influence the other instantaneously, a concept that Einstein famously referred to as spooky action at a distance. Importantly, this phenomenon does not violate the speed of light limit set by relativity, as no useful information is transmitted during the entanglement process. Instead, it emphasizes the fundamental differences between classical and quantum understanding of reality. In the cosmic context, quantum entanglement could have profound implications. For instance, when two particles become entangled in a specific region of space, and then one is sent to a different location, possibly across vast intergalactic distances, their entangled nature remains intact. This raises intriguing questions about the role of entanglement in the early universe, where particles likely interacted and became entangled before the universe expanded significantly. As galaxies and structures formed, these entangled pairs could persist for billions of years, potentially influencing the understanding of quantum states in distant regions. While entangled particles do not appear to communicate or send signals between themselves at astronomical distances, studies in quantum information theory suggest that entanglement could play a pivotal role in future technologies such as quantum computing and quantum communication. Efforts to leverage entanglement for practical uses, whether on Earth or in the cosmos, continue to explore its intriguing properties. The ongoing research into quantum entanglement not only challenges our perceptions of locality and reality, but also encourages us to rethink our understanding of the universe itself, bridging the gap between the smallest scales of quantum mechanics and the vastness of cosmic structures. Quantum superposition is one of the foundational principles of quantum mechanics, describing a phenomenon where a quantum system can exist in multiple states simultaneously until it is measured. This concept contrasts sharply with our everyday experiences, where objects occupy defined states. In the quantum realm, a single particle, such as an electron, can be in multiple positions, energies, or spins at the same time, and it is only upon measurement that the system collapses into one of these potential states. The reality of superposition can be illustrated through thought experiments, the most famous being Schrödinger's cat. In this scenario, a cat inside a sealed box is simultaneously alive and dead due to the fate of a radioactive atom that may or may not decay. Until an observer opens the box, the cat exists in a superposition of both states. This paradox highlights the strangeness of quantum mechanics and raises fundamental questions about the role of the observer and the nature of reality itself. Mathematically, superposition is represented using wave functions, which provide a complete description of a quantum system. These wave functions can be combined, and their resultant forms represent the various possible states of the particle. The coefficients in these combinations correspond to the probabilities of finding the system in a specific state upon measurement. For instance, a particle could be described by a wave function that places it in multiple locations, and the probability of detecting it in one location versus another is determined by the square of the amplitude of the wave function. As a system interacts with its environment, these superpositions can become entangled with other states, leading to decoherence, where the system effectively loses its quantum characteristics. This process is what helps to reconcile the quantum world with our classical experience, as superpositions cannot easily be observed when systems interact with their environments. Understanding quantum superposition not only provides profound insights into the behavior of particles at the smallest scales, but also plays a pivotal role in emerging technologies such as quantum computing and quantum cryptography, where the ability to exploit superposition could lead to revolutionary advancements. Reconciling quantum mechanics with general relativity is one of the most significant challenges in modern physics, as these two foundational theories describe the universe at vastly different scales and principles. Quantum mechanics governs the behavior of the very small, dealing with particles and their interactions, while general relativity describes the gravitational force and the structure of space-time on cosmological scales. The fundamental disparity lies in their treatment of gravity and the nature of space-time. In quantum mechanics, forces are described in terms of quantum fields and particles, with gravity being much weaker than the other fundamental forces. This leads to difficulties when trying to apply quantum principles to the curved space-time described by general relativity. General relativity treats gravity not as a force in a traditional sense, but as the curvature of space-time caused by mass and energy. This conceptual framework does not easily lend itself to the probabilistic nature of quantum phenomena, creating a divide between the two theories. Efforts to unify these frameworks have led to the development of theories such as quantum field theory in curved spacetime, which attempts to incorporate quantum mechanics into the general relativistic framework. However, this approach has limitations, particularly in extreme conditions like those found near black holes or during the Big Bang, where both quantum effects and strong gravitational forces come into play. At these scales, traditional physics breaks down, illustrating the need for a more comprehensive theory. Various candidates for such a unified theory have been proposed, with string theory and loop quantum gravity being among the most discussed. String theory posits that fundamental particles are not point-like objects, but rather tiny vibrating strings, potentially providing a framework that incorporates both quantum mechanics and general relativity. Loop quantum gravity, on the other hand, seeks to quantize spacetime itself, suggesting a granular structure of spacetime at the smallest scales. Both of these approaches are still under active investigation and face significant theoretical and experimental challenges. The quest for a cohesive theory that bridges quantum mechanics and general relativity continues to drive much of modern theoretical physics. Insights gained from this pursuit not only have the potential to enhance our understanding of the universe, but could also lead to groundbreaking discoveries about the very fabric of reality, the nature of black holes, and the origins of the universe itself. Quantum fluctuations are temporary changes in the amount of energy in a point in space, arising from the inherent uncertainties described by quantum mechanics. These fluctuations occur due to the uncertainty principle, which dictates that certain pairs of physical properties, like position and momentum, cannot be precisely determined simultaneously. In this framework, energy levels can fluctuate rapidly, resulting in brief appearances of virtual particles that pop in and out of existence. These fluctuations are crucial to our understanding of the universe, particularly in the context of cosmic events. In the very early universe, shortly after the Big Bang, quantum fluctuations played a significant role during the inflationary period. It is during this phase that the universe experienced an exponential expansion, smoothing out irregularities and leading to the large-scale structure we observe today. Fluctuations in energy density provided the seeds for the formation of galaxies and clusters, as they caused slight variations in gravitational attraction that eventually grew over time. Moreover, quantum fluctuations influence fields like particle physics, where they underlie processes such as Hawking radiation around black holes. In this scenario, particle-antiparticle pairs arise near the event horizon, and if one particle falls into the black hole while the other escapes, it results in the black hole losing energy and mass over time. This phenomenon has implications for the ultimate fate of black holes, suggesting that they could eventually evaporate entirely. The role of quantum fluctuations extends to everyday phenomena as well. They contribute to the zero-point energy of vacuum states and affect the behavior of superconductors, among other physical processes. As we probe deeper into the structure of matter and the forces that govern it, understanding quantum fluctuations remains essential in piecing together the broader narrative of how the universe evolved from its origins to its current state, highlighting the profound connection between the microscopic quantum world and the macroscopic cosmos. Quantum tunneling is a fascinating phenomenon where particles can pass through energy barriers that, according to classical physics, they should not be able to cross. This occurs due to the probabilistic nature of quantum mechanics, which allows particles to have a certain probability of being found in locations that are energetically unfavorable. For example, if a particle is confined in a potential well and encounters a barrier, there is a finite chance it will be found on the other side of that barrier, despite lacking the energy to overcome it in a classical sense. On a cosmic scale, quantum tunneling plays a critical role in many processes. One of the most notable examples is in the fusion reactions that power stars. In the core of a star, temperatures and pressures are immense. Here, hydrogen nuclei must overcome their mutual electrostatic repulsion to fuse into helium. The energy required to achieve this is substantial, yet quantum tunneling allows the nuclei to pop through the barrier created by this repulsion, facilitating the fusion process. Without tunneling, stellar fusion would occur at a much slower rate, affecting the evolution and lifespan of stars. Another cosmic manifestation of quantum tunneling can be found in the concept of the universe's birth during the Big Bang. Some theories suggest that the very emergence of space and time from a quantum state could involve tunneling from a higher dimensional space or false vacuum state into our observable universe. This means that the initial conditions of the universe could have been set through quantum processes, creating the framework for everything we know. Moreover, in the realm of black holes and Hawking radiation, quantum tunneling again makes an appearance. Virtual particles can emanate from the event horizon of black holes, with one particle falling in and the other escaping, effectively allowing black holes to lose mass over time. This phenomenon offers a fascinating glimpse into how quantum mechanics intersects with the vast scales of time and space, leading us to ponder the fundamental workings of our universe at its most mysterious levels. Quantum mechanics plays a critical role in understanding the evolution of black holes, particularly through the concept of Hawking radiation. Named after the renowned physicist Stephen Hawking, this phenomenon arises from the intricate dance of quantum mechanics at the event horizon of a black hole. It suggests that black holes can emit radiation due to the creation of particle-antiparticle pairs in the vacuum of space. This process allows one particle to fall into the black hole while the other escapes, leading to a gradual loss of mass. This concept challenges the classical view of black holes as entities from which nothing can escape. According to quantum mechanics, even within the incredibly strong gravitational fields surrounding black holes, fluctuations occur that create conditions for Hawking radiation to develop. As a result, black holes are not just passive objects. They can gradually shrink over time, potentially evaporating entirely if they do not acquire additional mass from surrounding matter. Additionally, the interplay between quantum mechanics and general relativity raises significant questions about the information paradox associated with black holes. When matter falls into a black hole, the classical theory suggests that all information contained within that matter is lost. However, quantum mechanics asserts that information cannot be destroyed. This paradox has led to ongoing debates in theoretical physics as scientists work to reconcile these two pillars of our understanding of the universe. The research surrounding black holes and quantum mechanics not only deepens our comprehension of these mysterious cosmic entities, but also pushes the boundaries of fundamental physics. The quest to understand how these concepts intertwine may ultimately reveal new insights into the fabric of space and time, painting a more complete picture of the evolution and fate of black holes in our universe. Quantum effects likely played a profound role in shaping the early universe, especially during the first moments following the Big Bang. At this time, the universe was in an extremely hot and dense state, where the laws of quantum mechanics dominated over classical physics. This environment was rich in particle-antiparticle pairs, which could spontaneously come into existence and annihilate each other due to the intense energy present. The fluctuating quantum fields at this stage may have influenced the distribution of energy and matter in the nascent cosmos, setting the stage for the large-scale structures we observe today. One of the significant consequences of these quantum effects is reflected in the process known as cosmic inflation. This theory posits that in the very early universe, a rapid exponential expansion occurred, smoothing out irregularities and distributing energy uniformly. Quantum fluctuations during this inflationary period would have been stretched to cosmic scales, leading to slight variations in density. These variations acted as seeds for the formation of galaxies and other structures as the universe continued to expand and cool. Furthermore, the nature of time and space itself may have been altered due to quantum mechanics. The connections between quantum field theory and general relativity suggest that space-time might exhibit quantum characteristics at very small scales. This notion challenges our classical understanding of causality and the continuity of space and time, making the early universe a laboratory for exploring the unknown interplay between these fundamental forces. As we delve deeper into the implications of quantum mechanics in the early universe, we confront profound questions about the beginning of time itself. How did reality emerge from a quantum state? What rules governed the universe when it was still young and incomprehensibly small? These inquiries not only enhance our knowledge of the universe's infancy, but may also lead us to new physics that bridges the gaps between the quantum realm and the cosmological landscape. Quantum gravity is a theoretical framework aimed at reconciling general relativity, which describes gravity on a large scale, with quantum mechanics, which governs the behavior of particles at the smallest scales. The challenge arises because, while general relativity explains how gravity influences the fabric of space-time, quantum mechanics deals with discrete particles and their interactions, leading to radically different predictions. This gap signifies one of the most significant unresolved issues in modern physics: how to formulate a coherent theory that encompasses both the forces of the very small and the very large. Several approaches are being explored to develop a theory of quantum gravity. One prominent candidate is string theory, which proposes that the fundamental building blocks of the universe are not point particles, but rather tiny, vibrating strings. These strings can exist in multiple dimensions, and their vibrational states give rise to various particles and forces. If string theory proves successful, it could provide a framework that unifies gravity with the other fundamental forces, namely electromagnetism and the strong and weak nuclear forces. Another leading candidate is loop quantum gravity, which seeks to quantize space-time itself. It posits that space is made up of discrete units called loops, thus introducing a granular structure at the smallest scales. This theory aims to preserve the principles of general relativity while incorporating quantum mechanics, potentially leading to a new understanding of gravitational phenomena, such as black holes and the Big Bang. The unification of these theories could vastly reshape how we perceive the universe. What we call gravity might not be merely a force, but rather the result of geometric properties of space-time influenced by quantum mechanics. This understanding could resolve long-standing questions about the nature of black holes and the singularities often associated with them. Ultimately, the quest for quantum gravity is not only about merging theories, it is about unlocking a deeper understanding of the universe's fundamental fabric and the interplay between its most basic constituents. Ultra-high-energy cosmic rays are some of the most energetic particles observed in the universe, with energies exceeding 1 billion trillion electron volts. These cosmic rays are primarily protons, although they can also consist of heavier atomic nuclei. Their origins remain a tantalizing mystery and are a subject of ongoing research. One of the leading theories attributes their production to extreme astrophysical phenomena such as supernova explosions, active galactic nuclei, and gamma-ray bursts. Supernovae are stellar explosions that occur when massive stars exhaust their nuclear fuel and undergo gravitational collapse. During these events, shock waves are generated, accelerating particles to extraordinarily high energies. The surroundings of these explosive remnants can serve as sites where cosmic rays are continuously accelerated, giving rise to those ultra-high energy particles that we detect on Earth. Active galactic nuclei are another promising source of ultra-high energy cosmic rays. These are regions around supermassive black holes found at the centers of galaxies, where intense gravitational forces and accretion of matter lead to the release of enormous amounts of energy. As matter spirals into the black hole, it can emit powerful jets of particles, which may accelerate protons and heavy nuclei to ultra-high energies. Observational evidence suggests that some of the most energetic cosmic rays correlate with specific active galaxies, reinforcing this connection. Moreover, gamma-ray bursts, which are among the most powerful explosions in the universe, could also be significant contributors. These bursts release enormous amounts of energy in the form of gamma rays, and the processes behind these events are thought to involve extreme environments capable of accelerating particles to mind-boggling speeds. The study of ultra-high energy cosmic rays not only sheds light on their origins, but also provides information about the most violent and energetic processes occurring in the universe, offering a window into the extreme physics governing these celestial phenomena. Cosmic rays significantly influence planetary atmospheres and can have various effects on life. These high-energy particles, mainly protons and heavier nuclei from outer space, continually bombard Earth's atmosphere, interacting with atmospheric gases and producing secondary particles including muons and neutrinos. Although most cosmic rays are absorbed or deflected by the atmosphere and magnetic fields, their interactions can lead to complex processes that affect both the atmosphere and biological systems. In the atmosphere, cosmic rays contribute to the production of certain isotopes, such as carbon-14 through nuclear reactions. This carbon isotope plays a crucial role in radiocarbon dating, which scientists use to determine the age of organic materials. The influence of cosmic rays extends beyond isotopes. They can also affect atmospheric chemistry. For instance, cosmic ray interactions can lead to the formation of clouds by ionizing molecules in the atmosphere. These changes in cloud formation can ultimately influence weather patterns and climate. The impact on life is multifaceted. While the Earth's atmosphere provides a protective shield against most cosmic rays, the radiation still reaches the surface, where it can pose a risk to living organisms. High levels of cosmic rays can lead to increased mutation rates in plants and animals. This radiation exposure can cause damage to cellular structures and DNA, raising concerns for evolutionary adaptations. However, some researchers suggest that the perpetual presence of cosmic rays might also contribute to the generation of genetic diversity, providing a potential advantage for evolution in a changing environment. In addition to their direct effects on life, cosmic rays are believed to contribute to broader biological phenomena, including cloud seeding and climate variability. These interactions remind us of the interconnectedness of cosmic events and terrestrial life, demonstrating how even forces from beyond our planet can have cascading effects on our environment and the biological processes that sustain life. As we learn more about cosmic rays and their impact on our planet, we gain a deeper appreciation for the complexities of life within the vast universe. The most powerful gamma-ray bursts are considered among the most energetic events in the universe, releasing an extraordinary amount of energy in just a few seconds. These bursts can outshine entire galaxies temporarily, producing gamma rays that travel vast distances across the cosmos. The leading causes of these phenomena are often linked to cataclysmic events related to massive stars and the dynamics of supernova explosions. One primary cause of gamma-ray bursts is the collapse of massive stars into black holes. When a very massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. As the core implodes, it may form a black hole, while the outer layers explode outward in a supernova. During this process, jets of extremely energetic particles can be generated and are focused along the rotational axis of the collapsing star. When these jets break out of the star and penetrate the outer layers, they emit intense gamma radiation, creating what we observe as a gamma-ray burst. Another significant origin of gamma-ray bursts is the merging of binary neutron stars. Neutron stars are incredibly dense remnants of supernovae, and when two of these stars spiral towards each other and eventually coalesce, the resulting event can produce a gamma-ray burst. Similar to collapsing massive stars, the merger can create powerful jets that emit gamma radiation. This type of burst is also often associated with kilonova events, which result from the ejection of material during the merger, leading to the creation of heavy elements such as gold and platinum. The study of gamma-ray bursts not only illuminates the dramatic end-of-life stages for massive stars, but also plays a crucial role in our understanding of the universe. These events serve as cosmic beacons, providing insights into the distribution of heavy elements and the mechanisms of star formation and death. As scientists continue to investigate these powerful bursts, they uncover more about the violent processes that shape the universe and the intricate interactions between matter and energy at extreme scales. Cosmic rays, which are primarily composed of protons and other atomic nuclei, reach nearly the speed of light through various acceleration processes in astrophysical environments. The mechanics behind this acceleration are complex and often involve phenomena associated with extremely energetic events in the universe. The most significant mechanisms at play include shock waves from supernovae, interactions within active galactic nuclei, and the dynamics of stellar processes. One of the primary processes responsible for cosmic ray acceleration is associated with supernova shocks. When a massive star explodes as a supernova, it generates powerful shock waves that rapidly expand into the surrounding space. As these shock waves travel through the interstellar medium, they interact with particles present in the environment. This interaction can result in particles gaining energy as they are pushed back and forth across the shock front, with each crossing leading to an increase in speed. This process is known as diffusive shock acceleration, and it can propel particles to extraordinarily high energies, sometimes reaching thousands of times greater than those achieved in Earth-based particle accelerators. Active galactic nuclei, which are regions surrounding supermassive black holes at the centers of galaxies, also produce powerful jets that can accelerate particles to near-light speeds. As matter falls into these black holes, it can form an accretion disk and emit energy in the form of jets that are directed away from the black hole. These jets are made up of high-energy particles and can be potent sources of cosmic rays, accelerating them to relativistic speeds as they travel outward into space. Additionally, other astrophysical events, such as gamma-ray bursts and pulsar winds, contribute to the acceleration of cosmic rays. Gamma-ray bursts, which result from catastrophic star collapses or neutron star mergers, release immense energy that can accelerate particles across vast distances. Pulsars, which are rotating neutron stars emitting beams of radiation, also create environments where particles can gain significant energy through magnetic field interactions. Through these processes, cosmic rays become some of the fastest particles in the universe, providing insights into high-energy astrophysics while influencing matters such as atmospheric chemistry and the conditions for life on Earth. Understanding how cosmic rays achieve such remarkable speeds helps unravel the complexities of the universe and the mechanisms that govern its dynamics. The highest energy neutrinos detected on Earth are believed to originate from some of the most extreme and energetic processes in the universe. Neutrinos are neutral particles that interact very weakly with matter, making them incredibly difficult to detect. However, their elusive nature allows them to pass through vast amounts of material, including entire planets, before interacting with other particles. The sources of these high-energy neutrinos are linked primarily to cosmic events such as supernovae, active galactic nuclei, and gamma-ray bursts. One significant source of high-energy neutrinos is supernovae, particularly those involving massive stars. During a supernova explosion, immense amounts of energy are released, leading to the production of neutrinos as byproducts of nuclear reactions. This process, coupled with the gravitational collapse of the star's core, generates a vast flux of neutrinos that can travel across space. If a supernova occurs close enough to our planet, its neutrino emissions could be detected on Earth. Another important source is active galactic nuclei, which are powered by supermassive black holes at the centers of galaxies. These regions experience extreme gravitational forces, driving gas and matter into accretion disks, where particles are accelerated to near the speed of light. Alongside this, powerful jets are emitted from these black holes, creating conditions suitable for high-energy neutrino production. The interactions within these jets can produce high-energy neutrinos, some of which may eventually reach Earth. Gamma-ray bursts, the most powerful explosions observed in the universe, are also suspected to be prolific sources of high-energy neutrinos. These bursts are associated with massive stellar collapses or the merger of compact objects like neutron stars. During these explosive events, conditions arise that can accelerate particles and generate neutrinos as a result of interactions within the explosion. Researchers have observed potential correlations between gamma-ray bursts and high-energy neutrinos, providing further evidence of their connection. As scientists continue to improve neutrino detection technologies, the study of these elusive particles sheds light on the most energetic processes in the cosmos. By identifying and characterizing the sources of high-energy neutrinos, researchers gain insights into fundamental astrophysical phenomena and the workings of the universe at its most extreme scales. Cosmic rays, high-energy particles from outer space, interact with interstellar and intergalactic magnetic fields in complex and intriguing ways. As cosmic rays travel through space, they encounter these magnetic fields, which can significantly alter their paths. The effects of this interaction depend on the energy of the cosmic rays and the strength of the magnetic fields they encounter. When cosmic rays move through interstellar magnetic fields, they can experience a phenomenon known as magnetic deflection. Charged particles, such as protons and atomic nuclei, will spiral around the magnetic field lines, causing their trajectories to curve rather than travel in straight lines. This deflection makes it challenging to trace the original sources of cosmic rays, as they may come from distant galaxies or supernova remnants, but appear to arrive from different directions due to the influence of magnetic fields. This effect is particularly prominent at lower energies, as higher energy cosmic rays have more momentum and are less significantly deflected. In addition to deflection, cosmic rays can also induce secondary interactions when they collide with magnetic field lines. These interactions can lead to the production of secondary particles and electromagnetic radiation. For example, when cosmic rays collide with interstellar hydrogen or helium atoms, the resulting interactions can generate showers of secondary particles, including muons and neutrinos, along with emissions across a spectrum that includes gamma rays. This process helps researchers understand the complex interplay between cosmic rays and their surroundings. On a larger scale, cosmic rays also interact with intergalactic magnetic fields, which are present but relatively weak compared to their interstellar counterparts. The low density of particles in intergalactic space means that cosmic rays have fewer collisions and interactions. However, over vast distances, cosmic rays can still be deflected by these faint magnetic fields. Even minor deviations can become significant over such distances, complicating efforts to trace the origins of ultra-high-energy cosmic rays back to their sources. The interaction between cosmic rays and magnetic fields not only informs our understanding of these energetic particles, but also enhances our comprehension of the structure and behavior of the universe at both interstellar and intergalactic scales. As scientists continue to unravel these complex dynamics, they gain deeper insights into the fundamental processes that shape our cosmic environment. Cosmic rays serve as valuable messengers, providing insights into the composition and properties of distant galaxies. As high-energy particles originating from various astrophysical processes travel through space, they carry information about their sources and the environments from which they came. By analyzing cosmic rays detected on Earth, scientists can infer details about the elemental and isotopic composition of these far-off galaxies. One way cosmic rays reveal information about distant galaxies is through their elemental composition. When cosmic rays interact with the Earth's atmosphere, they produce secondary particles that can be detected by advanced instrumentation. By studying the ratios of different elements in cosmic rays, such as carbon, iron, and helium, researchers can gain insights into the nucleosynthesis processes occurring in their sources. These processes occur in stars and their explosions, providing clues about how elements were forged in previous generations of stars and the chemical evolution of their host galaxies. Moreover, cosmic rays can help inform scientists about the environments in which they were accelerated. For instance, extreme environments, such as those found in supernova remnants and active galactic nuclei, produce high-energy cosmic rays. The acceleration mechanisms that create these particles depend on the physical conditions of their surroundings. By analyzing the energies and distributions of cosmic rays, researchers can infer the conditions such as temperature, density, and magnetic field strengths in their source regions. This information can lead to a better understanding of the interplay between cosmic rays and the matter surrounding them. Cosmic rays also play a role in studying the propagation of particles through interstellar and intergalactic mediums. As they travel through these regions, they undergo interactions with the ambient matter and radiation, which can affect their composition and energy. By understanding how cosmic rays lose energy and what alterations occur during their journey, scientists can refine their models of cosmic ray sources and enhance the accuracy of their conclusions regarding distant galaxies. Overall, cosmic rays can tell us much about the composition and characteristics of distant galaxies, acting as crucial tools for astrophysicists. Their study enhances our understanding of cosmic evolution, the life cycles of stars, and the broader dynamics of galaxies in the universe. This ongoing research continues to unveil the complex story behind the formation and evolution of cosmic structures. Cosmic rays have a significant influence on star formation and galactic evolution, affecting processes at both local and galactic scales. These high-energy particles, predominantly composed of protons and heavier nuclei, can interact with gas and dust in interstellar space, playing a crucial role in the dynamics of the interstellar medium. Their interactions can alter both the properties of molecular clouds and the conditions under which new stars form. One of the primary effects of cosmic rays is their ability to ionize the gas in molecular clouds. As cosmic rays penetrate these dense regions, they can ionize atoms and molecules, which in turn can influence the chemistry of the cloud. This ionization enhances the formation of certain molecules, such as molecular hydrogen, which is a critical component for star formation. Additionally, the energy deposited by cosmic rays can contribute to the heating of the gas, creating turbulence that affects how gas collapses to form stars. Without the influence of cosmic rays, molecular clouds would behave differently, potentially altering the rate of star formation within galaxies. Furthermore, cosmic rays participate in the regulation of galactic dynamics. Their pressure can serve as a counterbalance to gravitational forces in the interstellar medium. When galactic gas is compressed by cosmic rays, it might offset the gravitational pull that would otherwise lead to the collapse of gas into stars. In this way, cosmic rays could modulate the efficiency and rate of star formation across different regions of a galaxy, contributing to the diversity of stellar populations observed. On a larger scale, cosmic rays can influence galactic evolution by affecting the feedback mechanisms that regulate the growth and life cycles of galaxies. The energy injected into the interstellar medium by cosmic rays can drive outflows of gas, impacting the gas content of galaxies and their ability to form new stars. This feedback loop may lead to variations in star formation rates and the chemical enrichment of galaxies, shaping their overall evolution. The interplay between cosmic rays, star formation, and galactic evolution is a complex and dynamic process. As scientists continue to explore these relationships, they uncover new aspects of how these high-energy particles contribute to the life cycles of stars and the formation of galaxies, adding another layer to our understanding of the universe's evolution. The unexpected dimming of Tabby's star, officially designated KIC 81221, has fascinated astronomers since its discovery. Initially noted for its peculiar and significant fluctuations in brightness, this star has become a subject of intense study and speculation regarding potential causes. While the exact mechanism behind its dimming remains uncertain, several theories have been proposed to explain this enigmatic behavior. One leading hypothesis suggests that the dimming could be caused by a cloud of dust or debris orbiting Tabby's star. If there are irregularities in the structure of a circumstellar disk, it could periodically block the light from the star, leading to the observed dips in brightness. This dust could be composed of various materials, including carbon-rich particles that absorb starlight more efficiently, resulting in noticeable dimming when they pass in front of the star. Another possibility is that the dimming could be related to the presence of a swarm of comets. If a group of comets were perturbed into an orbit that takes them close to the star, their passage could result in periodic darkening. The idea is that the cometary materials could partially obscure the starlight as these bodies move in and out of alignment with our line of sight. This scenario could lead to the random and unexpected dimming patterns observed over time. A more exotic explanation involves the presence of an enormous structure, such as a Dyson sphere, built by an advanced civilization. This hypothetical megastructure would be designed to capture a star's energy, but the theory remains highly speculative and lacks substantial supporting evidence. While intriguing, this idea is often viewed with skepticism compared to more conventional astrophysical explanations. As research continues, scientists use telescopes and observational data to gather more insights into Tabby's star and its peculiar behavior. The ongoing study of this star serves as a reminder of the complexities of stellar dynamics and the vast unknowns that persist in our understanding of the universe. Each new piece of information brings us closer to resolving the mystery of Tabby's star and deepening our comprehension of stellar phenomena. Magnetars are a type of neutron star known for their incredibly strong magnetic fields, which can exceed 1 trillion Gauss, approximately 1,000 times stronger than an ordinary neutron star. The generation of these formidable magnetic fields is attributed to a combination of stellar evolution processes and the dynamics of nuclear matter under extreme conditions. The origin of a magnetar's magnetic field begins with the collapse of a massive star during a supernova explosion. When a star with sufficient mass exhausts its nuclear fuel, it undergoes gravitational collapse, leading to the formation of a neutron star. As the core collapses, its rotation rate increases due to the conservation of angular momentum. This rapid rotation, coupled with the extreme density of the matter, facilitates the generation of magnetic fields through a process known as the dynamo effect. In the case of magnetars, this dynamo mechanism operates under conditions unique to neutron stars. The extreme densities and the presence of superfluid and superconducting matter allow for the efficient amplification of magnetic fields. As the neutron star rotates, charged particles in its interior also move, generating electric currents that can strengthen and organize the magnetic field lines. Magnetars can also experience rapid changes in their rotation and magnetic field configuration over time, contributing to the creation of their powerful fields. Additionally, the intense magnetic fields associated with magnetars may also result from the continued evolution of the neutron star's magnetic structure post-formation. As the star cools and contracts, the magnetic field lines can become compressed, further increasing their strength. The complex interactions within this environment can lead to shifting configurations of the magnetic field, leading to stronger localized concentrations of magnetic energy. The study of magnetars not only elucidates the processes responsible for their extreme magnetic fields, but also provides insight into the behavior of matter and energy under conditions that cannot be replicated on Earth. These enigmatic celestial objects serve as laboratories for testing our understanding of fundamental physics, and their unique properties challenge our knowledge of magnetic phenomena in the cosmos. Supernovae in massive stars are triggered by the complex interplay of nuclear processes occurring at the end of a star's life cycle. As these stars exhaust their nuclear fuel, they undergo significant changes that ultimately lead to these spectacular explosions. The two primary types of supernovae associated with massive stars are core collapse supernovae and type second supernovae, both of which stem from the same basic process. In massive stars, those typically with at least 8 times the mass of the Sun, nuclear fusion occurs in successive layers as the core contracts and heats up. Initially, hydrogen is fused into helium in the core, and as hydrogen is depleted, helium fusion begins. This layering continues as heavier elements are formed, with carbon fusing into oxygen, then oxygen into silicon, and so on, until iron begins to accumulate in the core. Iron fusion does not produce energy. Instead, it consumes energy, leading to a buildup of this non-fusible material. Once a massive star's iron core reaches a critical mass, it can no longer withstand the force of gravity. At this point, catastrophic collapse occurs. The core implodes within seconds, compressing to extremely high densities, which generates immense temperatures and pressures. This collapse results in a shockwave that propagates outward through the star's outer layers. When this shockwave reaches the surface of the star, it rebounds and leads to the explosive ejection of the star's outer material, resulting in a supernova explosion. Additionally, there are other mechanisms that can trigger supernova in massive stars. If a massive star is part of a binary system, it may siphon material from its companion star, leading to an increase in mass that can ultimately cause collapse. In some cases, this transfer can trigger instability and initiate the supernova process even before the star has fated itself through its own internal nuclear processes. The spectacular explosion of a supernova not only marks the end of a massive star's life, but also has far-reaching implications for the universe. These events distribute heavy elements into space, contributing to the formation of new stars and planets, and drive the dynamics of the cosmic environment. Through the study of supernovae, astronomers gain essential insights into stellar evolution and the life cycle of materials in the cosmos. Most stars meet a dramatic end through supernova explosions, but a select few manage to survive this cataclysmic event. The key to their survival lies in their mass and the process surrounding the explosion. Stars that undergo supernovae typically deplete their nuclear fuel, leading to an unstable core that collapses under gravity, triggering a violent explosion. However, there are instances where a star, particularly those in binary systems, can avoid total destruction. When a massive star is part of a binary system, it can transfer some of its mass to its companion star before the supernova event. This transfer can enable the surviving star to escape the gravitational collapse that leads to a supernova. The dynamics of the interaction between the two stars can play a critical role in determining whether one will remain intact. Another fascinating aspect is the type of supernova involved. Type 1 supernovae occur in binary systems when a white dwarf accretes enough material to reach a critical mass and ignite a catastrophic explosion. The companion star may survive this process if it is sufficiently distant, avoiding the explosion's direct impact. Conversely, Type 2 supernovae result from the core collapse of a massive star. Depending on the mass and structure of the star, the supernova can leave behind a neutron star or a black hole, while the outer layers may scatter into space. Moreover, some stars may end their life cycle in a less explosive manner, transitioning smoothly into processes that do not result in a supernova at all. This realm of stellar evolution highlights the complexity and fascinating nature of the cosmos, where survival is often a combination of mass, fate, and cosmic interactions that shape the destiny of these celestial giants. Fast radio bursts, often referred to as FRBs, are among the most intriguing mysteries in modern astrophysics. These brief and intense bursts of radio waves can last only a few milliseconds, yet they release vast amounts of energy, equivalent to the energy produced by the sun over a span of several days. The origins of these enigmatic signals are still a topic of intense research, but scientists have proposed several potential causes. One leading hypothesis suggests that FRBs may be the result of tremendous astrophysical events, such as the merging of compact objects like neutron stars or black holes. During these violent mergers, immense amounts of energy are released, creating conditions that can generate the rapid bursts of radio waves that we detect. Another possibility involves the activity of magnetars, which are neutron stars with extraordinarily strong magnetic fields. The theories suggest that the intense magnetic fluctuations in magnetars could result in these powerful radio emissions. FRBs are detected from deep space and their sources remain elusive, as only a fraction has been localized to specific galaxies. In many cases, astronomers have pinpointed FRBs to locations within distant galaxies, often associating them with star-forming regions. This connection raises further questions about the relationship between such cosmic bursts and the life cycles of stars. The transient nature of fast radio bursts makes them particularly challenging to study, and their unpredictable occurrence adds to the intrigue. They were first discovered in 2007, and since then, hundreds of events have been observed, increasing our understanding of these phenomena. As technology advances and more observations are gathered, we inch closer to unlocking the secrets behind these cosmic puzzles, paving the way for a deeper understanding of the universe and its myriad processes. Binary star systems, which consist of two stars orbiting around a common center of mass, experience a captivating evolutionary journey. These systems come in various types, influenced by factors such as mass, separation distance, and their initial formation conditions. Over time, the gravitational interplay between the stars dictates their evolution, leading to a series of fascinating transformations. In widely separated binary systems, the stars may evolve relatively independently, following their own life cycles. Each star will exhaust its nuclear fuel at different rates, depending on its mass. More massive stars typically evolve faster than their lower mass companions. As they age, they enter different stages such as becoming red giants or ending their lives as white dwarfs, neutron stars, or black holes. The outcome depends on the mass of the stars involved, resulting in diverse evolutionary tracks. In closer binary systems, the interaction between the stars can profoundly affect their evolution. When one star becomes a red giant, it can transfer material to its companion star through a process called mass transfer. This exchange can significantly alter the life cycle of both stars, potentially rejuvenating the smaller mass star and impacting the evolution of the larger mass star. This interaction can lead to unique phenomena such as novae, or even type Ia supernovae if one star becomes a white dwarf and gains enough mass. Ultimately, the fate of binary systems can be quite dramatic. They may end as a pair of white dwarfs, or one star might fully consume the other, creating a single massive object. The gravitational interactions could also force them into even closer orbits, leading to the potential for exotic outcomes, including gravitational waves should they eventually collide. The complex dynamics of binary star systems not only yield stunning results across the cosmos, but also enhance our understanding of stellar evolution and the forces at play in the universe. Strange quark stars are a fascinating and exotic theoretical type of compact star, composed primarily of strange quarks. To understand their nature, we first need to consider the building blocks of matter. Ordinary matter consists of protons and neutrons, which in turn are made up of three types of quarks: up, down, and strange quarks. Strange quarks are heavier than up and down quarks, and they play a crucial role in the formation of these unique stellar objects. The phenomenon of strange quark stars is rooted in the incredibly dense conditions found in neutron stars. Neutron stars typically result from the remnants of massive stars after a supernova explosion, and they are composed predominantly of neutrons held together by gravity. Under certain extreme conditions, however, the density can become so great that the up and down quarks within the neutrons can convert into strange quarks. This leads to the formation of a strange quark matter environment, where strange quarks become more stable and can create a new state of matter. Strange quark stars are theorized to have distinctive properties, mainly because of the strange quark matter's unique equation of state. In these stars, the presence of strange quarks allows for a more compact structure than that of ordinary neutron stars, potentially making strange quark stars less massive yet denser. This could yield remarkable gravitational effects. Some researchers suggest that these stars might be able to spin rapidly without becoming unstable, leading to considerable differences in their observed characteristics. Currently, the existence of strange quark stars remains hypothetical, as no conclusive observational evidence has been found to confirm their presence. However, astrophysical phenomena associated with neutron stars, such as certain types of pulsars and gravitational waves from neutron star mergers, have spurred interest in the study of strange quark stars. Understanding these objects could significantly enhance our knowledge of the fundamental forces and behaviors governing matter under extreme conditions, enriching our grasp of the universe's most compact and enigmatic entities. The formation of stars in extreme environments, particularly in the chaotic and densely packed centers of galaxies, is a process shaped by unique conditions that differ significantly from those in quieter regions of space. At the heart of many galaxies lies a supermassive black hole, surrounded by a hot, dense cloud of gas and dust, as well as high-energy radiation and gravitational forces. These extreme conditions play a critical role in the star formation process. In these galactic centers, the volume of gas and dust is immense, and interactions between particles can lead to complex dynamics. High temperatures can initially inhibit star formation by keeping the gas in a heated state. However, shock waves and interactions caused by the presence of the black hole can compress nearby gas clouds, creating regions where the conditions become favorable for star formation. As these clouds collapse under their own gravity, they can fragment into smaller pieces, ultimately leading to the birth of new stars. Another critical factor is the influence of stellar feedback from existing stars. In such extreme environments, the massive stars that form typically evolve rapidly and can go supernova, injecting energy and material back into the surrounding medium. This feedback can further compress gas, triggering additional bursts of star formation in a cycle of creation and destruction. The interplay between the intense gravitational forces and the energy released by stellar evolution can promote the formation of clusters of stars very quickly. Additionally, the presence of strong magnetic fields and turbulent motions within the dense environment can also influence star formation. These factors contribute to varying star formation rates and the potential for forming different types of stars, from massive, short-lived behemoths to smaller, long-lived ones. The study of star formation in these extreme settings not only broadens our understanding of stellar evolution, but also reveals insights into the dynamics and characteristics of galaxies themselves, showcasing the extraordinary environments where star formation can thrive despite the challenges posed by their surroundings. The cosmic microwave background radiation, often referred to as the CMB, is a remnant of the early universe, specifically from about 380,000 years after the Big Bang. One of the most striking features of the CMB is its remarkable uniformity, showing only slight variations in temperature across the sky. This near uniformity raises fascinating questions about the history and structure of the universe. The uniformity of the CMB can be traced back to the conditions of the early universe, shortly after the Big Bang. In this hot, dense state, the universe was filled with a nearly uniform sea of particles interacting through radiation. As it expanded, the universe cooled, allowing protons and electrons to combine into hydrogen atoms, marking the epoch of recombination. At this point, photons could travel freely without being constantly scattered by charged particles. The release of these photons created the CMB, which has since redshifted into the microwave range as the universe continued to expand. However, the CMB is not perfectly uniform. It exhibits slight temperature fluctuations or anisotropies. These variations are crucial because they provide insights into the density fluctuations in the early universe, which later evolved into the large-scale structures we observe today, such as galaxies and clusters of galaxies. The uniformity evident in the CMB can be understood through the theory of inflation, which posits that a rapid expansion occurred in the very early universe. This inflationary phase smoothed out inhomogeneities, leading to the relatively even distribution of matter and radiation we see in the CMB. The statistical properties of the CMB, including its uniformity, indicate that the universe is isotropic and homogeneous on large scales, meaning it looks the same in all directions and at large distances. These characteristics support the cosmological principle, a fundamental assumption in cosmology. The CMB serves not only as a remnant of the early universe, but also as a vital tool for understanding the evolution of the cosmos, providing a snapshot of conditions that laid the groundwork for the formation of galaxies and large-scale structures. The shape of the universe is a profound topic that encompasses fundamental concepts in cosmology. Understanding the true shape involves considering the universe's large-scale structure and its geometric properties. As researchers study the cosmos, They explore different models, typically describing the universe as either flat, open, or closed. The shape is closely tied to the universe's overall density and the influence of gravity. T. Current observations, particularly from the cosmic microwave background radiation, suggest that the universe is very close to flat on a large scale. In a flat universe, the geometry follows the rules of Euclidean space, meaning that parallel lines never meet and the angles in a triangle sum to 180 degrees. This flatness implies that the total density of the universe is close to a critical density, where the gravitational pull of all matter and energy balances the expansion rate. However, the universe could also be curved, either positively or negatively, based on its total density. A positively curved universe resembles the surface of a sphere, where parallel lines may eventually converge. In contrast, a negatively curved universe resembles a saddle shape, where parallel lines can diverge. The actual density of matter and energy in the universe dictates which of these scenarios is true, and currently available evidence indicates that most of the universe's matter is dark energy, which accelerates its expansion. Additionally, there are intriguing theories proposing that the universe could be multidimensional or structured in a more complex topology, such as a toroidal shape or even higher dimensional manifolds. These concepts remain speculative but reflect the quest for a deeper understanding of the universe's nature. Ultimately, the true shape of the universe remains an active area of research, one that continues to challenge our perceptions and deepen our understanding of the cosmos and its fundamental structure. The question of whether there are regions of the universe with different physical laws is both intriguing and complex. Our current understanding of physics is based on principles that have been rigorously tested and confirmed here on Earth and in our observable universe. These principles, including the laws of gravity, electromagnetism, and nuclear physics, seem to operate consistently across the cosmos. However, some theories propose scenarios where variations might occur. One concept arises from the idea of a multiverse, where our universe is just one of many that may exist with potentially differing physical laws or constants. Each universe in this multiverse might have its own unique set of conditions that govern the behavior of matter and energy. For example, variations in fundamental constants like the gravitational constant or the strength of electromagnetic interactions could lead to entirely different physical realities in other universes. However, this remains a speculative area of research, as it is difficult to test or observe these other universes directly. Another aspect comes into play at the edges of our knowledge, such as extreme conditions found near black holes or during the formation of the universe itself. These areas may challenge our current understanding of physics, and scientists hypothesize that under such extreme scenarios, familiar laws might not apply or could behave differently. Conditions such as high energy densities could lead to phenomena not fully explained by existing theories, and researchers are actively studying these transitions. Quantum mechanics also introduces the notion of uncertain and probabilistic behavior, which can give rise to strange outcomes even within regions of our universe that adhere to established physical laws. While on a grand scale the laws of physics appear uniform, the underlying quantum processes can lead to variations in behavior at microscopic and macroscopic levels. While the consensus among physicists is that the same physical laws, as we understand them, govern our universe, the frontiers of theoretical physics encourage exploration and questioning of this idea. Ongoing research and observations continue to refine our understanding of the cosmos, keeping the door open for new revelations about the nature of reality itself. The formation of the first stars and galaxies occurred during a pivotal moment in the history of the universe, often referred to as the cosmic dawn. This era took place roughly 300 million to 500 million years after the Big Bang, when the universe began to cool sufficiently to allow hydrogen and helium gas to condense and coalesce under the influence of gravity. Initially, the universe was a vast expanse of hot, diffuse gas composed primarily of hydrogen and helium. As it expanded, it cooled, leading to a gradual decrease in temperature. Over time, tiny fluctuations in density created regions where gas began to clump together. The gravity from these denser regions attracted more matter, forming larger and larger clouds of gas. As these gas clouds collapsed, they became increasingly dense and hot, eventually reaching temperatures high enough to initiate nuclear fusion, marking the birth of the first stars. These primordial stars, often referred to as population 3 stars, were vastly different from the stars we see today. They were likely more massive, hotter, and more luminous, and they contained almost no heavy elements since those had not yet formed. The energy produced by these first stars resulted in a process called stellar nucleosynthesis, where lighter elements were fused into heavier ones. When these massive stars reached the end of their life cycles, they underwent supernova explosions, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. As the first stars exploded, they expelled this enriched material into their surroundings, influencing the structure and composition of the universe. This process led to the formation of the first galaxies, as groups of star-forming regions began to accumulate and coalesce. These galaxies served as the building blocks for larger structures, and over billions of years, they evolved into the complex cosmic web we observe today. The vast formations of galaxies, clusters, and superclusters that make up the universe. The study of the first stars and galaxies is an active field of research, with astronomers utilizing powerful telescopes and simulations to probe the origins of these luminous objects and the role they played in shaping the universe. Understanding how these early structures formed sheds light on the evolution of the cosmos and the processes that led to the rich diversity of galaxies we observe in the present day. Cosmic inflation is a theory that proposes a rapid expansion of the universe in the very early moments following the Big Bang. This expansion is thought to have occurred in a fraction of a second, specifically from approximately 10 to the negative 35th seconds to 10 to the negative 32nd seconds after the Big Bang. The idea behind inflation is that a small, homogeneous region of space underwent an exponential expansion, dramatically increasing the size of the universe. The nature of cosmic inflation is based on the need to explain several observed properties of the universe, such as its large-scale uniformity and flatness. Without inflation, the universe would exhibit significant inhomogeneities due to quantum fluctuations. Cosmic inflation offers a solution by stretching these fluctuations and smoothing out the universe, leading to the homogeneous and isotropic cosmos we observe today. Additionally, inflation predicts that tiny density variations, which would later evolve into the large-scale structures of galaxies and clusters, originated from quantum fluctuations in the inflationary field. Recent evidence supports the inflationary model, particularly through observations of the cosmic microwave background radiation, which displays slight temperature variations indicative of density fluctuations. These fluctuations align with predictions made by inflation theory, suggesting an early inflationary stage in the universe's history. Advanced techniques, including the measurement of primordial gravitational waves, hint at inflation's potential as well. However, while inflation remains the leading theory to explain early universe conditions, some details about its exact cause and mechanism remain uncertain, leading to various inflationary models. Ongoing research aims to refine our understanding of inflation and confirm its occurrence as theorized. Observations from instruments like the Planck satellite and future missions will be critical in providing insights into the validity and specifics of the inflationary scenario, ultimately improving our comprehension of the universe's origins. The Hubble tension refers to the discrepancy observed between different measurements of the universe's expansion rate, characterized by the Hubble constant. This constant measures how fast galaxies are receding from us due to cosmic expansion. Two primary methods have led to different values for the Hubble constant, creating a challenge for cosmologists seeking to understand the precise nature of our universe. One method involves observing the cosmic microwave background radiation from the early universe, particularly using measurements from satellites like the Planck Observatory. This approach relies on the standard model of cosmology, which includes assumptions about the contents and behavior of the universe. According to this method, the Hubble constant is estimated to be about 68 kilometers per second per megaparsec. In simpler terms, this means that for every megaparsec of distance from us, galaxies are receding at approximately 68 kilometers per second. In contrast, astronomers have also employed local distance ladder techniques, which measure the Hubble constant by observing nearby supernovae and using them as standard candles. This method yielded a higher value of about 73 kilometers per second per megaparsec. This tension between the two figures raised significant questions regarding our understanding of cosmic expansion and the fundamental properties of the universe. To address this Hubble tension, researchers are exploring several avenues. One possibility involves re-examining the systematic uncertainties associated with both measurement techniques, as discrepancies could arise from errors in distance measurements or calibration methods. Additionally, some investigations focus on understanding potential new physics beyond the standard model of cosmology, such as the role of dark energy, modifications to gravity, or the existence of unknown particles that might influence expansion rates. Another approach involves gathering more precise data through improved observations, such as those from the James Webb Space Telescope and other advanced facilities. By refining the measurements of distant supernova and accurately determining distances to various cosmic objects, scientists hope to gain more insight into the Hubble constant and resolve the tension. While the Hubble tension remains a significant challenge, it also represents an exciting opportunity for deeper understanding, potentially leading to groundbreaking discoveries about the universe's structure and expansion. The largest structures in the cosmic web, which includes galaxies, clusters of galaxies, and superclusters, are formed through a combination of gravitational attraction, dark matter, and complex processes of cosmic evolution. The evolution of these structures is rooted in the fundamental dynamics of the universe, starting from the moment of the Big Bang. Initially, the universe was nearly uniform, composed of hot, dense plasma. However, quantum fluctuations during this early period led to slight variations in density, creating regions where matter began to clump together under the influence of gravity. Dark matter, which makes up a significant portion of the universe's total mass, played a crucial role in this process. Unlike ordinary matter, dark matter does not interact electromagnetically and thus cannot be seen directly, but its gravitational effects are profound. Over time, these clumps of dark matter acted as scaffolding for baryonic matter, allowing gas and dust to collapse into denser regions and form stars and galaxies. As galaxies formed, they began to group together due to gravitational attraction, forming larger structures like galaxy clusters. These clusters can contain numerous galaxies bound together by their mutual gravity, and they serve as the building blocks for even larger formations, such as superclusters. The interactions between these various cosmic structures also contribute to their evolution. Galaxies can merge, pass by one another, or interact gravitationally, leading to the redistribution of matter and the formation of new structures. Additionally, the cosmic web itself is characterized by a filamentary structure, where galaxies and clusters are aligned along enormous filaments of dark matter, surrounding vast voids with relatively few galaxies. This web-like arrangement is a result of the gravitational forces at play and reflects the large-scale structure of the universe. Over billions of years, as the universe expanded and evolved, the interplay of dark matter, baryonic matter, and gravitational forces forged the intricate network of galaxies, clusters, and superclusters we observe today. The study of the cosmic web and its largest structures not only helps us understand the distribution of matter in the universe, but also sheds light on the underlying physics that governs cosmic evolution. Ongoing observational efforts, including deep-field surveys and advancements in cosmological simulations, continue to enhance our comprehension of these colossal formations and their significance in the larger context of the universe. The missing baryon problem refers to the observation that there is significantly less baryonic matter, ordinary matter made up of protons, neutrons, and electrons, observed in the universe than what theoretical models predict. Baryons make up stars, gas, and galaxies, yet observational evidence suggests that a considerable portion of baryonic matter remains undetected. This discrepancy raises important questions about the distribution and behavior of baryonic matter in the cosmos. The missing baryons were expected to exist primarily in the form of hydrogen and helium gas, especially in the intergalactic medium. Theoretical models based on observations of the cosmic microwave background radiation and the large-scale structure of the universe suggest that the amount of baryonic matter should be around 15 to 20% of the total mass energy content of the universe. However, direct observations account for only about half of that predicted quantity, leading to the problem. Several explanations have been proposed to account for the missing baryons. One of the leading hypotheses is that baryonic matter is primarily found in a warm, diffuse state, making it challenging to detect with current observational methods. This gas may exist in so-called filaments that connect galaxies and clusters in the cosmic web, but are too faint to be observed directly, especially at optical wavelengths. Observations in the X-ray and ultraviolet spectra have begun to reveal the presence of this warm-hot intergalactic medium, suggesting that a significant fraction of missing baryons may reside in these diffuse regions. Another possibility involves the presence of baryons in small-scale structures. They could exist within star-forming regions that are not sufficiently resolved in many observational surveys, leading to an underestimation of the amount of baryonic matter in the universe. Additionally, processes such as stellar feedback, where massive stars expel gas back into the intergalactic medium, also complicate the inventory of baryonic matter. Astrophysicists continue to tackle the missing baryon problem through improved observational techniques and simulations, providing a better understanding of how baryonic matter is distributed and behaves in the universe. As advanced telescopes and instruments become available, researchers increasingly refine their estimates and gather data on the elusive baryons, working towards resolving this fundamental mystery in the quest to understand the cosmos comprehensively. The concept of quantizing spacetime arises from efforts to reconcile general relativity, which describes gravity as a curvature of spacetime, with quantum mechanics, which governs the behavior of particles at the smallest scales. This pursuit aims to create a unified framework that can describe the fundamental forces of nature within a single theoretical model. The idea that spacetime could be quantized suggests that instead of being a continuous fabric, it may be composed of discrete units, or quanta. One prominent approach to quantizing spacetime is found in loop quantum gravity. This theory posits that space is made up of tiny discrete loops that quantize the geometry of spacetime. In this model, the gravitational field is represented by a network of interconnected loops, creating a granular structure to space at the Planck scale, which is incredibly small, about 10 to the negative 35 meters. These loops would give rise to a quantized aspect of space, potentially resolving certain paradoxes associated with black holes and singularities in traditional general relativity. Another avenue of exploration is string theory, which posits that fundamental particles are not point-like objects, but rather one-dimensional strings. In this framework, the vibrations of these strings determine the particle's properties. String theory naturally leads to a multi-dimensional space where additional dimensions are compactified. While it does not directly quantize space-time in a traditional sense, it offers a framework in which quantum mechanics and gravity can coexist, suggesting that space-time itself could emerge from more fundamental string dynamics. The challenge of demonstrating the quantization of space-time lies in the need for experimental verification. Currently, the scales at which quantum gravitational effects would become noticeable are far beyond the reach of existing technology. Scientists are exploring various avenues, including high-energy particle collisions and astrophysical phenomena like black holes, hoping to find observable effects that may hint at the discrete nature of space-time. As theoretical physicists continue to develop these models, the question of whether space-time can be quantized remains an open and active area of research. Achieving a successful theory of quantum gravity could profoundly change our understanding of the universe, offering insights into its fundamental nature and the relationship between gravity and the other forces governing particle behavior. The investigation into this deep question continues to inspire both curiosity and innovative ideas about the fabric of reality. The true nature of gravity at the quantum level remains one of the most profound questions in modern physics. While general relativity describes gravity as the curvature of spacetime caused by mass, this macroscopic view is not readily compatible with the principles of quantum mechanics, which govern the behavior of particles at the subatomic scale. The challenge has been to develop a coherent framework that unites these two seemingly distinct areas. At the heart of this discussion lies the concept of how gravity operates within the quantum realm. One approach is to consider the hypothetical particle known as the graviton, which is proposed to mediate gravitational interactions, much like photons mediate electromagnetic interactions. If gravitons exist, they would be massless, traveling at the speed of light, and would operate within a framework similar to quantum field theory. However, despite extensive theoretical work, direct evidence for gravitons has yet to be found. Current theories also explore the effects of quantum mechanics on gravitational phenomena. For example, the idea of quantum entanglement suggests that space-time itself could be a manifestation of information and entanglement at a fundamental level. This perspective positions gravity not as a classical force, but as an emergent property of underlying quantum states. In this view, gravitational interactions may not require a specific particle, but could arise from more fundamental aspects of quantum mechanics. Loop quantum gravity presents an alternative approach where the geometry of spacetime is quantized. In this theory, space is described as a network of discrete loops, and gravity emerges from the geometry formed by these loops. This approach offers insights into phenomena such as black hole entropy and singularities, suggesting a finite structure to spacetime that could mitigate issues present in classical general relativity. Despite the promising theories, the empirical study of quantum gravity faces significant challenges. The energy scales at which quantum gravitational effects become apparent are unattainable with existing technology. However, advances in observational astronomy, such as studying gravitational waves and high-energy cosmic events, could provide indirect evidence that informs our understanding of gravity at the quantum level. Ultimately, achieving a full theory of quantum gravity would revolutionize our understanding of the universe, potentially revealing insights into its fundamental structure and the relationship between gravity and quantum mechanics. The journey toward this unifying framework is ongoing, with physicists exploring diverse theories and approaches in an effort to uncover the true nature of gravity at the quantum scale. The idea of additional spatial dimensions beyond the three we experience in our daily lives is a fascinating concept in modern physics. According to string theory, which proposes that the fundamental building blocks of the universe are one-dimensional strings rather than point-like particles, there could be as many as 10 or 11 dimensions. These additional dimensions are not directly observable because they may be compactified or curled up at scales much smaller than we can currently perceive. To visualize this, think of how a garden hose appears to be one-dimensional from a distance, yet has a circular cross-section that defines its additional dimension. Similarly, while our universe seems to consist of three large dimensions, length, width, and height, these extra dimensions could exist in a manner that is closed off or too tiny to notice with our instruments. As a result, while we navigate our familiar three dimensions, the other dimensions could fundamentally influence the laws of physics. These higher dimensions can have significant implications for understanding gravity and the fundamental forces. For instance, they allow for theories that attempt to unify gravity with the other fundamental forces of nature, which has been an enduring challenge in physics. The behavior of particles and the interactions that we observe may stem from the dynamics of these extra dimensions. The exploration of higher dimensions challenges our understanding of reality and invites intriguing questions about the origins of the universe, the nature of space and time, and the fundamental structure of everything around us. As scientists continue to investigate these ideas, they may unveil more about the complexities of the universe we inhabit and the hidden layers that operate beyond our everyday perception. In the strongest gravitational fields, such as those near black holes or neutron stars, gravity behaves in ways that stretch our understanding of the universe. According to Albert Einstein's theory of general relativity, gravity is not just a force but a curvature of space-time caused by mass. This means that massive objects warp the fabric of space-time around them, affecting how other objects move through that region. Near a black hole, the gravitational field is so intense that it creates a point of no return known as the event horizon. Once an object crosses this boundary, it cannot escape the black hole's pull, not even light. This phenomenon leads to exotic effects, such as time dilation, where time appears to move slower for an object close to the black hole compared to an observer far away. This effect has been confirmed in less extreme situations, but the effects become extreme near a black hole, illustrating how gravity can influence the very nature of time. In the vicinity of neutron stars, which are incredibly dense remnants of supernova explosions, gravity can create a phenomenon called gravitational waves. These ripples in space-time occur when massive objects accelerate, such as when two neutron stars spiral toward each other. When they collide, they release enormous energy, producing gravitational waves that travel across the cosmos. Detecting these waves has opened a new window into astrophysics, allowing scientists to observe events that were previously undetectable. Understanding how gravity operates in these extreme environments is crucial for physicists. It helps to refine our models of fundamental physics and challenges our concepts of reality. As we delve deeper into the mysteries of strong gravitational fields, we continue to uncover the deep relationship between mass, space, and time, expanding our grasp of the universe's workings. Gravitational waves are generated by the acceleration of massive objects, especially in dynamic and extreme astrophysical scenarios. When two massive bodies, such as black holes or neutron stars, orbit one another, they create disturbances in space-time that propagate outward at the speed of light. This phenomenon occurs because these massive objects warp the fabric of space-time as they move, generating ripples much like a stone thrown into a pond creates waves on the water's surface. The collision of these objects produces some of the most powerful gravitational waves imaginable. When black holes merge, for example, the energy released is equivalent to several solar masses converted entirely into energy as a result of their collision. This not only gives rise to gravitational waves, but also emits electromagnetic radiation, allowing observers to study these extraordinary events through multiple astronomical lenses. Gravitational waves provide unique insights into the universe that are difficult to obtain through traditional means. They allow for the observation of events that are invisible in regular light. For instance, merging black holes can be detected purely through the gravitational waves they produce, without any accompanying electromagnetic signature. This ability to hear the universe through these waves opens up new ways to study the cosmos, including the formation and evolution of compact objects, the behavior of matter under extreme conditions, and the expansion of the universe. Furthermore, analyzing the characteristics of gravitational waves can reveal information about their sources, such as their masses and spins. As gravitational wave astronomy continues to advance, it can help answer fundamental questions about the nature of gravity, the formation of black holes, and the environments in which they exist. The pursuit of understanding gravitational waves exemplifies how innovative scientific techniques deepen our comprehension of the fundamental workings of our universe. Wormholes are fascinating theoretical structures in the fabric of space-time that connect disparate points in the universe, creating shortcuts for travel between them. According to general relativity, wormholes could exist due to the warping of space-time caused by extreme gravitational fields. The concept was first introduced in the early 20th century, and while wormholes remain primarily theoretical, their implications capture the imagination of scientists and science fiction enthusiasts alike. There are different types of wormholes, but one of the most well-known is the Einstein-Rosen bridge, which suggests a tunnel-like structure connecting two separate regions of space-time. For a wormhole to form, an immense amount of mass energy would be required to stabilize the throat, ensuring it remains open and traversable. This leads to interesting possibilities regarding exotic matter, a hypothetical form of matter that would possess negative energy density. Such exotic matter could counteract the gravitational forces attempting to close the wormhole, allowing for its potential stability. As intriguing as the concept may be, the formation of natural wormholes is purely speculative at this stage. While scientists have explored the equations governing their existence, no empirical evidence has been found to confirm that they can form naturally in the universe. Discussion around their existence often revolves around extreme astrophysical events, such as those surrounding black holes, but even those scenarios remain theoretical. If wormholes could exist, they would challenge our understanding of time and space, and might even offer pathways for time travel. However, the specifics of traversing a wormhole, including the consequences and technical challenges, are still left to the realms of theoretical physics. As we continue to study the universe's mysteries, wormholes remain a captivating subject, bridging the gap between what we know and the vast, unexplored possibilities of our cosmos. White holes are theoretical counterparts to black holes in the realm of general relativity. While black holes draw everything in due to their immense gravitational pull, white holes are proposed to do the opposite. They are imagined as regions of space-time that expel matter and energy rather than absorbing them. Essentially, a white hole would release all the matter and radiation that a black hole has collected, offering a reverse functionality. The concept of a white hole arises from the equations of general relativity, particularly when one considers the idea of a wormhole connecting a black hole and a white hole. In this framework, matter that enters the black hole could theoretically emerge from the white hole in another part of the universe or even in a different universe altogether. This intriguing notion adds a layer of complexity to our understanding of space-time and could imply interconnectedness between separate cosmic locations. However, despite the fascinating theoretical nature of white holes, there is currently no observational evidence to support their existence. The physical properties required for a stable white hole create significant challenges. For instance, if a white hole were to exist, it would need to be surrounded by an event horizon, similar to a black hole, but it would constantly eject matter in a highly controlled manner. Such a situation poses questions about the stability and persistence of such an object in the universe. While the idea of white holes is captivating and invites speculation about the boundaries of our universe, they remain a speculative concept within theoretical physics. The search for understanding continues, with scientists eager to uncover the fundamental nature of black holes, space-time, and the cosmos. But as of now, white holes exist only in the framework of mathematical theories rather than as observable entities. At the singularity of a black hole, space-time exhibits some of the most extreme and perplexing behaviors in the universe. The singularity is the point at the center of a black hole, where gravitational forces compress matter to an infinitely dense state, and the laws of physics as we understand them break down. It represents a culmination of matter and energy becoming concentrated beyond the limits of our current scientific frameworks. In the vicinity of the singularity, general relativity predicts that the curvature of space-time becomes infinite. This means that the traditional concepts of time and space lose their usual meaning. As one approaches the singularity, the gravitational pull intensifies, causing time to stretch significantly. An outside observer would see time almost halt for any object nearing the singularity, while from the infalling object's perspective, it would experience the passage of time as normal until it reaches the singular point. The nature of space-time changes dramatically inside a black hole. The usual geometric properties determined by general relativity no longer work as expected, leading to paradoxes and divergent predictions. For example, the laws of classical physics suggest that once an object passes the event horizon, the boundary surrounding a black hole, it is irrevocably pulled toward the singularity, where known physics cannot fully describe what happens next. This breakdown of physics raises fundamental questions about the very nature of reality. To fully understand the behavior of space-time at the singularity, scientists seek a theory of quantum gravity that would unite general relativity with quantum mechanics, potentially offering a clearer picture of what occurs at these extreme conditions. As research continues, the singularity remains one of the most profound mysteries of our universe, reflecting not only on the limits of our current understanding, but also on the potential for groundbreaking discoveries in the future of cosmology. The origin of Earth's water has been a subject of extensive research and debate within the scientific community. The predominant theories suggest that water on our planet has two main sources: outgassing from volcanic activity and contributions from extraterrestrial bodies such as comets and asteroids. Outgassing refers to the release of water vapor from the Earth's interior through volcanic eruptions. During Earth's early formation, the planet was molten, and volcanic activity was rampant. As the surface cooled, water vapor released from the mantle, and volcanic eruptions condensed to form surface water, pooling in the planet's basins. This process could have contributed a significant portion of the water that we see today. The second theory posits that water was delivered to the early Earth from external sources, particularly through the impacts of icy celestial bodies. Comets, known for their high water content, are prime candidates for delivering water to our planet. Similarly, certain types of asteroids, which contain hydrated minerals, may have also contributed to Earth's water inventory. The prevailing view suggests that these impacts were more common during the early solar system, a period referred to as the late heavy bombardment, and would have introduced substantial amounts of water to the planet. Recent research continues to explore the isotopic compositions of water found in different celestial bodies. Comparing these ratios with those of Earth's water helps scientists unravel the specific contributions of these various sources. While the exact proportions of water from each source remain uncertain, the combination of outgassing and contributions from celestial impacts paints a compelling picture of how Earth became a watery planet. Understanding the origins of Earth's water not only sheds light on our own planet's history, but also informs the search for water in other parts of the universe, potentially pointing to habitable conditions elsewhere. Venus, often referred to as Earth's twin due to its similar size and composition, presents a strikingly different environment compared to our planet. This divergence primarily arises from variations in atmospheric conditions, geological activity, and proximity to the Sun. While both planets share some initial characteristics, the evolutionary paths taken over billions of years have led to their stark contrasts. One of the most significant differences lies in Venus's atmosphere. Venus is enveloped in a thick, toxic layer of carbon dioxide with clouds comprised of sulfuric acid. This dense atmosphere creates a runaway greenhouse effect, trapping heat and resulting in surface temperatures that can soar to around 800 degrees Fahrenheit. In stark contrast, Earth has a balanced greenhouse effect, maintaining temperatures suitable for life. The unregulated climate of Venus has rendered it exceedingly hostile, with pressures at the surface over 90 times that of Earth's atmosphere. Geologically, Venus also diverges from Earth. While both planets have volcanoes, historical records suggest that Venus displays signs of volcanic activity that are far more volatile and widespread than Earth's. The surface of Venus is relatively young, indicating that it has undergone significant resurfacing events, possibly due to extensive volcanic activity. In contrast, Earth's geology is marked by plate tectonics, which recycle the crust and contribute to a diverse range of geological features and a more dynamic climate. Additionally, the difference in their distances from the Sun plays a crucial role. Venus is closer to the Sun, leading to higher solar radiation and consequently more dramatic climate effects. This proximity affects not only temperature but also influences the chemical reactions occurring in the atmosphere. As scientists continue to study Venus, they gain insights into planetary evolution and the variable conditions that can lead to the emergence or absence of life. Understanding the differences between Venus and Earth can also enhance our knowledge of exoplanets and the potential for life beyond our solar system. Mars once had a robust magnetic field and a thicker atmosphere, which helped create conditions potentially favorable for life. However, various factors have contributed to the loss of both over time, transforming Mars into the cold and arid planet we see today. The transition from a more Earth-like world to its current state has intrigued scientists seeking to understand planetary evolution. One of the primary reasons for Mars losing its magnetic field lies in its core structure. Unlike Earth, which has a liquid outer core that generates a strong magnetic field through the dynamo effect, Mars appears to have a smaller and less active core. Studies suggest that Mars may have had a magnetic field early in its history, generated by convective motion in its molten core. However, as the planet cooled, this core may have solidified, leading to a shutdown of the dynamo effect and the eventual loss of its protective magnetic field. Without a strong magnetic field, Mars became vulnerable to solar wind, a stream of charged particles emitted by the Sun. This interaction erodes the planet's atmosphere over time. The solar wind strips away high-energy particles and gases from the Martian atmosphere, gradually diminishing its thickness. Unlike Earth, which has a magnetic field to shield it from such solar activity, Mars lacks this defense, leading to the atmosphere being carried away into space. The combined effects of a weak magnetic field and the continuous bombardment by solar wind resulted in significant atmospheric loss. Estimates indicate that Mars may have lost most of its atmosphere over hundreds of millions of years, transitioning from a warmer, wetter environment to the thin atmosphere we observe today. This dramatic transformation has profound implications for the planet's potential habitability and serves as a reminder of how differing geological and internal processes can shape planetary environments. As space missions continue to investigate Mars, researchers hope to uncover more about its history and the factors that influenced its evolution. The interiors of gas giants such as Jupiter and Saturn are vastly different from terrestrial planets like Earth. Their compositions primarily comprise hydrogen and helium, with trace amounts of other elements and compounds. This composition is a product of the planet's formation, which occurred in the outer regions of the solar system where lighter gases were abundant. Understanding the makeup of these massive planets provides insights into their structures, atmospheres, and magnetic fields. The structure of a gas giant can be divided into several distinct layers. The outermost layer is the atmosphere, which consists primarily of hydrogen and helium, along with clouds of ammonia, water vapor, and other compounds. Below the atmosphere lies a deep layer of metallic hydrogen. At extremely high pressures found in this region, hydrogen is compressed into a metallic state, exhibiting properties similar to a metal. This metallic hydrogen layer is responsible for the strong magnetic fields associated with these gas giants. Beneath the metallic hydrogen layer, gas giants are thought to have a rocky or icy core, which may contain heavier elements like silicon, sulfur, and oxygen, along with water ice and other compounds. The core can be substantial, potentially comprising a mass several times greater than that of Earth. However, due to the immense pressure and high temperatures, the exact nature of this core remains a topic of ongoing research. The interactions between these layers contribute to the unique phenomena observed on gas giants. The dynamics of their atmospheres, including powerful storms like the Great Red Spot on Jupiter and the intricate cloud patterns seen on Saturn, arise from the extreme conditions within and above their atmospheric layers. By studying gas giants, scientists continue to gather clues about planet formation, the behavior of materials under extreme conditions, and the potential for discovering exoplanets that share similarities with these majestic giants. The Kuiper Belt and the Oort cloud are two distinct regions of our solar system, consisting of icy bodies and remnants from its formative years. Their formation is closely linked to the processes that shaped the early solar system, which began approximately 4.6 billion years ago. The Kuiper Belt lies just beyond the orbit of Neptune and is populated with numerous small icy bodies, including dwarf planets like Pluto. This region is thought to have formed from the protoplanetary disk of gas and dust that surrounded the young sun. As material in the disk began to coalesce, some of that matter formed the gas giant planets, while the remaining debris, in a region beyond the giant planets, became the Kuiper Belt. Over time, these icy bodies collided and accumulated, creating a diverse collection of objects that have remained relatively unchanged since the early solar system. The gravitational influences of nearby Neptune played a crucial role in shaping the dynamics of this region, preventing these icy bodies from coalescing into a larger planet. In contrast, the Oort cloud is theorized to be a vast spherical shell of icy objects situated much farther from the Sun, extending up to a light year away. It is believed to have formed from material that was expelled from the inner solar system during the formative years of its evolution. When the giant planets, particularly Jupiter and Saturn, migrated in their orbits, their gravitational interactions scattered many smaller icy bodies outward. Some of these objects were pushed into distant orbits far from the Sun, resulting in the formation of the Oort cloud. This region serves as a reservoir for long-period comets, which can orbit the Sun and sometimes enter the inner solar system if perturbed by gravitational interactions. The differences in structure, location, and origin between the Kuiper Belt and the Oort cloud provide valuable insights into the dynamics of our solar system's formation and evolution. The study of these regions continues to reveal the stories of the early solar system, guiding our understanding of planetary formation and the potential for similar structures in other star systems. As new missions and observations target these distant realms, they promise to enhance our knowledge of the building blocks of our cosmic neighborhood. Oumuamua, discovered in late 2017, is recognized as the first known interstellar object to pass through our solar system. Its name, derived from the Hawaiian word for scout or messenger, reflects its origin from beyond our solar neighborhood. The discovery sparked significant interest and debate among astronomers regarding its true nature, as it exhibited several peculiar characteristics that set it apart from typical asteroids or comets. Comet, despite a lack of the expected cometary tail. The absence of typical cometary features raised questions about whether Oumuamua had outgassed volatile materials. Some researchers suggested that it could be a fragment of a larger body ejected from its home star system, while others proposed more exotic theories regarding its origin. The object's high speed and trajectory indicate that it had originated from another star system, potentially traveling for millions of years before entering ours. This suggests that Oumuamua could offer a glimpse into the conditions and materials present in distant star systems, compelling scientists to consider the broader context of how celestial bodies may interact and evolve in different environments. Despite extensive observations, many questions about Oumuamua remain unanswered. Its precise composition, shape, and the reasons behind its unusual acceleration continue to be points of investigation. The debates surrounding its identity highlight the excitement of exploring unique cosmic phenomena and push the boundaries of our understanding of interstellar space. As we continue to study this remarkable visitor, we may not only uncover the secrets of Oumuamua, but also gain insights into the nature of the countless objects lingering in the vast expanses of the cosmos. Uranus is unique among the planets in our solar system due to its extreme axial tilt, which causes it to rotate on its side at an angle of approximately 98 degrees. This unusual orientation suggests a turbulent history involving significant collisions or gravitational interactions that profoundly affected its rotational dynamics. One prevailing theory proposes that Uranus experienced a series of massive impacts during its formative years. These collisions could have involved large protoplanetary bodies or other celestial objects that struck the planet at oblique angles, resulting in a shift of its axis. This radical shift would have altered Uranus's rotational axis to the extreme position we observe today. Such a scenario is plausible considering the chaotic environment of the early solar system, where planetary bodies were still colliding and forming. Another possibility is that Uranus's tilt was influenced by interactions with its own extensive system of moons and rings. The gravitational pull of these bodies might have contributed to the planet's sideways rotation over time. The interplay of gravitational forces within this system could have played a role in maintaining or enhancing the axial tilt after the initial impact had occurred. The result of Uranus's sideways rotation is equally fascinating. Each pole experiences about 21 Earth years of continuous sunlight, followed by an equivalent period of darkness as the planet orbits the Sun. This extreme tilt affects the planet's climate and weather patterns, leading to interesting phenomena in its atmosphere, which has been observed to have variable weather systems. Understanding why Uranus rotates on its side not only sheds light on the planet itself, but also serves as a window into the violent history of our solar system, encompassing the processes of planetary formation and evolution. The hexagonal storm at Saturn's North Pole is one of the most striking phenomena in our solar system. This mysterious six-sided pattern, which measures about 15,000 miles across, is a fascinating feature that has intrigued scientists since it was first observed by the Voyager missions in the early 1989s. Understanding the forces behind this unusual structure provides insights into the dynamics of Saturn's atmosphere and the behavior of gas giant planets as a whole. The hexagon is primarily a result of differential rotation in Saturn's atmosphere, where the winds at various latitudes move at different speeds. The specific dynamics of the atmosphere create a standing wave pattern which can stabilize the hexagonal shape. Some researchers believe that this formation is similar to the behavior of fluid dynamics observed in rotating fluid systems, where the interactions between faster and slower moving air can lead to the development of regular patterns. Additionally, the stability of the hexagonal shape is likely reinforced by the interaction of the high-speed jet streams surrounding it. The hexagon is situated in a region of the atmosphere where a powerful eastward jet stream flows at around 125 miles per hour. This jet stream helps maintain the hexagonal formation by providing a consistent force that organizes the atmospheric flow into this distinctive pattern. Curiously, the hexagon seems to persist over long periods, demonstrating remarkable stability compared to other storms. This stability might be attributable to the immense scale of the hexagonal structure, which allows it to endure despite variations in the surrounding atmosphere. Recent observations from the Cassini spacecraft, which studied Saturn from 2004 to 2017, have provided valuable data that enhances our understanding of the hexagon and its behavior. The hexagonal storm at Saturn's North Pole remains a captivating example of atmospheric phenomena, illustrating the intricate interactions that can occur in the atmospheres of gas giants and offering clues to the complex fluid dynamics that govern these distant worlds. The idea that life could have originated multiple times on Earth is a fascinating notion that challenges our understanding of the origins of life. Current scientific theories suggest that the origins of life likely resulted from complex chemical processes that led to the emergence of simple biological systems. Given the right conditions, it is conceivable that these processes could have occurred independently in different environments, leading to multiple beginnings of life. Some researchers propose that life may have emerged first in various habitats, such as hydrothermal vents on the ocean floor, shallow pools, or even within ice on the planet's surface. Each of these environments could provide unique sets of chemical precursors and energy sources essential for the formation of organic compounds and ultimately primitive life forms. The diverse conditions on early Earth might have supported parallel pathways for life to arise, allowing for the possibility of multiple origin events. There is also the concept of extremophiles, organisms that thrive in extreme conditions, which suggests that life's biochemical processes can be remarkably versatile. If simple life forms were able to emerge in diverse environments, it opens the door to the possibility that later interactions or competitions among these life forms could have led to a single lineage dominating as it evolved over time. This concept is underpinned by the principle of competitive exclusion, which suggests that one life form may outcompete another for resources, leading to the predominance of a single branch of life. However, despite the theoretical appeal of multiple origins of life, there is currently no direct evidence to support this idea. Most of the evidence we have points to a single origin of a common ancestor from which all current life on Earth descended. The field of astrobiology continues to explore these concepts, as understanding how life might arise and evolve in various environments sheds light on our own origins and informs the search for life beyond our planet. Each discovery about early microbial life on Earth helps refine our hypotheses about the origin and evolution of life, fueling ongoing inquiries into this profound question. Panspermia is the hypothesis suggesting that life, or at least the building blocks necessary for life, could be distributed throughout the universe by comets, asteroids, or meteoroids. This concept raises intriguing possibilities about how life might spread between celestial bodies, potentially seeding life on planets like Earth. Over the years, scientists have explored the likelihood and mechanisms of panspermia, weighing its implications for the presence of life beyond our planet. One argument in favor of panspermia is the resilience of microbial life. Certain extremophiles can withstand harsh conditions, including intense radiation, extreme temperatures, and vacuum. This extraordinary adaptability suggests that microorganisms could survive the journey through space, potentially even embedded within meteorites. Some studies propose that these organisms could remain dormant for an extended period, reactivating upon landing in a more favorable environment, such as a planet with suitable conditions for life. Additionally, there is evidence that celestial bodies can exchange material. For instance, asteroid impacts on a planet can eject debris into space, which may eventually collide with another planet. On rare occasions, Earth could receive material from Mars and vice versa. Such mechanisms highlight the feasibility of cross-planetary contamination, supporting the notion that life might transfer between planetary bodies within our solar system and potentially beyond. Shisa. However, panspermia does not answer the fundamental question of how life originated. If life arrived on Earth through this means, it still raises the question of where and how that life began in the first place. The hypothesis mainly emphasizes the potential for life to spread rather than its initial creation. While panspermia offers a plausible mechanism for the distribution of life, the actual likelihood of life traveling significant distances through space and successfully establishing itself on another planet remains uncertain. Current research continues to investigate the resilience of microorganisms in space conditions and the mechanisms that facilitate such transport. As we explore our solar system and beyond, the search for signs of life and the pursuit of understanding the origins of life, whether on Earth or from elsewhere, reinforces the profound possibilities implied by the panspermia hypothesis. The limits of life in extreme environments are continually being tested and expanded by scientific research. Life on Earth has demonstrated remarkable adaptability, thriving in a variety of extreme conditions. These environments include extreme temperatures, pressures, acidity, saline concentrations, and radiation levels. Studying organisms that inhabit these harsh conditions, known as extremophiles, provides fascinating insights into the limits of life as we know it. One of the most extreme environments on Earth is found in hydrothermal vents on the ocean floor. Here, organisms exploit chemical energy from sulfur compounds and thrive in temperatures exceeding 300 degrees Fahrenheit. These thermophiles and hyperthermophiles demonstrate the ability of life to survive and flourish in high heat, where conventional life forms would cease to function. Similarly, organisms called psychrophiles can endure freezing temperatures as low as -38 degrees Fahrenheit, showcasing life's resilience in frigid conditions. Acidic environments such as acid mine drainage sites host acidophiles that thrive in pH levels as low as 0. Conversely, certain halophiles thrive in highly saline environments such as salt flats and salt lakes, demonstrating how organisms can adapt to extreme concentrations of salt. These adaptations often involve unique biochemical and structural modifications, allowing these organisms to maintain cellular function and stabilize their proteins and membranes under such adverse conditions. However, there are limits to these adaptations. For instance, beyond certain thresholds of pressure, temperature, or radiation, the fundamental biological processes such as DNA replication, protein synthesis, and cellular metabolism can fail. The boundaries of life are often defined by the fragility of complex biological molecules and the intricate balance of biochemical reactions necessary for sustaining life. Extreme radiation poses another challenge as it can damage DNA and cellular structures, leading to lethal consequences for life as we understand it. Studying extremophiles not only expands our understanding of the limits of life on Earth, but also informs the search for life beyond our planet. If life can thrive in environments previously deemed inhospitable, such as the icy moons of Jupiter and Saturn, then the potential for discovering life in similarly extreme conditions elsewhere in the universe becomes more plausible. As researchers continue to explore these frontiers, the concept of life's boundaries is continually evolving, reshaping our understanding of what it means to be alive in this diverse cosmos. Defining life in a cosmic context involves considering a broad range of characteristics that capture the essence of living organisms, while also taking into account the diverse environments that may exist beyond Earth. In general, life is often characterized by several fundamental properties, including organization, metabolism, growth, reproduction, response to stimuli, and adaptation through evolution. However, as we explore the potential for extraterrestrial life, the challenge lies in determining how these criteria might apply in different environments and forms. At its core, life is defined by its ability to maintain homeostasis, a stable internal environment, despite changes in its external surroundings. This concept can encompass a wide variety of physiological processes. For instance, earthly organisms utilize biochemical pathways to convert energy from their environment, growth and reproduction mechanisms to perpetuate their species, and genetic systems to pass on information to future generations. In a cosmic context, we must consider that these processes could manifest differently in alien life forms, potentially relying on alternative biochemistries or even non-carbon-based compounds. The search for extraterrestrial life often includes a focus on environments that could support these life-sustaining properties. For example, scientists investigate places like subsurface oceans on icy moons and the atmospheres of exoplanets, seeking signs of metabolic processes or organic molecules that indicate potential life. Astrobiology aims to understand the conditions that might yield life, informing our approach to detecting signs of life elsewhere and broadening our definitions to include life forms that may be vastly different from our own. Additionally, the concept of life as we know it may be too limiting if we wish to account for the diversity of life forms that could exist throughout the universe. This opens the possibility that life could take forms based on alternative chemistries, such as silicon rather than carbon, or exist in environments that are not considered habitable by Earth standards. Therefore, in a cosmic context, the definition of life is an evolving concept that embraces the potential for a wide variety of life forms while still acknowledging the fundamental principles that define living systems. As researchers continue to explore the complexities of life and its potential forms in the universe, the definition of life remains a dynamic and thought-provoking topic, inviting ongoing inquiry and debate across multiple scientific fields. Each discovery brings us closer to realizing the vast possibilities of life beyond Earth and challenges our understanding of what it means to be alive in the cosmic tapestry. Comets and asteroids are significant players in the distribution of organic compounds throughout the solar system and potentially beyond. These celestial bodies, remnants from the early solar system, contain a wealth of materials, including water, organic molecules, and other essential compounds. Their interactions with planets can contribute to the delivery of these compounds, playing a vital role in the potential development of life. Comets are composed largely of ice and dust, and they are believed to hold primitive material from the solar system's formation. As they approach the Sun, comets become active, shedding gas and dust and forming a visible coma and tail. During this process, they can release organic compounds such as amino acids and other building blocks of life. When comets collide with planets, they can deliver these organic materials, essentially seeding the surface with compounds that are critical for the development of life. Asteroids, on the other hand, are primarily rocky bodies that can also contain a variety of organic materials. Some asteroids specifically are thought to be enriched with carbonaceous compounds, making them rich sources of organic molecules. When these asteroids impact a planet, they can transfer significant amounts of organic compounds and water, contributing to the overall chemical complexity necessary for life's origins. The study of meteorites, particularly carbonaceous chondrites, has revealed that many of the amino acids and other organic compounds found on Earth could also exist in these ancient space rocks. The notion that comets and asteroids could deliver the building blocks of life lends support to theories like panspermia, which suggest that life, or its precursors, could be transported across the cosmos. This underscores the potential for life to arise in diverse environments, not just on its planet of origin. Observations of organic material in comets, asteroids, and meteorites provide valuable insights into how these bodies might have contributed to the emergence of life on Earth and possibly elsewhere in the universe. As space missions and studies continue to focus on these intriguing bodies, scientists aim to unravel the complexities of how organic compounds are distributed and the implications for understanding life's origins. The discoveries made through the exploration of comets and asteroids deepen our knowledge of planetary chemistry and the potential pathways life could take throughout the cosmos. Planetary habitability is not a static condition. It evolves over long timescales due to a variety of factors that include geological activity, atmospheric changes, stellar evolution, and cosmic events. Understanding how these elements interact provides insights into the potential for a planet to support life throughout its history. One significant factor influencing habitability over time is the geological activity of a planet. On Earth, plate tectonics plays a crucial role in maintaining a stable climate and recycling nutrients essential for life. Over millions of years, geological processes can alter a planet's surface, creating diverse environments that may favor or hinder the development of life. In contrast, a planet that ceases geological activity may experience a decline in habitability as its atmosphere degrades and its surface becomes inhospitable. Atmospheric conditions are also critical in determining planetary habitability over time. For instance, early in Earth's history, its atmosphere evolved from a hostile environment dominated by carbon dioxide to one enriched with oxygen, facilitating the emergence of complex life. Changes in atmospheric composition can result from volcanic activity, biological processes, and extraterrestrial impacts. As a planet's atmosphere evolves, so too do its capabilities to support life. An atmosphere that becomes overly thick or toxic can render a once habitable world uninhabitable. Stellar evolution significantly impacts habitability as well. Over billions of years, stars undergo changes that influence their energy output and the conditions on surrounding planets. For example, as a star like our Sun ages, it will gradually increase in brightness, which could result in higher surface temperatures on Earth and potentially lead to the loss of its oceans. Such changes challenge the conditions necessary for life and prompt shifts in habitable zones, regions around stars where conditions are suitable for liquid water to exist. Furthermore, cosmic events such as asteroid impacts, supernovae, or shifts in a planet's orbit can introduce sudden changes that affect habitability. For instance, a catastrophic impact can lead to mass extinctions, drastically altering ecosystems and the course of evolution. Planetary habitability is a dynamic characteristic shaped by an interplay of internal and external factors over long timescales. By studying the history and evolution of habitability on Earth and other celestial bodies, scientists aim to understand the complex processes that govern life's potential to thrive in the universe. As we search for habitable exoplanets and other worlds, this knowledge informs the criteria we use to recognize environments where life might arise or persist. When searching for life beyond Earth, scientists focus on identifying potential biosignatures, indicators of past or present life, on exoplanets. These biosignatures can manifest in various forms, including chemical, physical, and biological signals that suggest biological processes may be at work. Here are some of the primary types of biosignatures researchers consider in the quest for extraterrestrial life. One of the most prominent biosignatures includes the presence of gases in a planet's atmosphere. On Earth, certain gases, such as oxygen and methane, exist in a delicate balance that is maintained by biological activity. The simultaneous presence of these gases could indicate biological processes, as oxygen typically depletes methane in the atmosphere unless there is a continual source of production. Other atmospheric gases, such as carbon dioxide, nitrous oxide, and ozone, can also signal biological activity, depending on their concentrations and contextual relationships. The detection of specific organic molecules is another important biosignature. Complex organic compounds such as amino acids, fatty acids, and hydrocarbons can hint at biological processes, especially when found in uncommon or unusual structures. These molecules can be produced through various geological or chemical processes, but the presence of a wide variety of organic compounds in significant amounts often signals biological origins. Surface conditions and geological features can also provide valuable biosignatures. For example, unusual surface features such as stromatolite-like formations could suggest past biological activity, similar to structures formed by microbial life on Earth. Additionally, signs of liquid water, whether in the form of oceans, lakes, or even subsurface aquifers, are crucial indicators of habitability and potential biosignatures, as water is fundamental to life as we know it. Lastly, isotopic ratios can serve as biosignatures. The ratios of certain isotopes can reveal biological processes, as organisms tend to preferentially utilize particular isotopes during metabolic processes. For instance, carbon isotopes can indicate biological activity based on their ratios found in organic matter. As technology advances, scientists are developing increasingly sophisticated instruments to analyze the atmospheres of exoplanets and study their chemical compositions. By identifying these potential biosignatures, researchers hope to uncover signs of life beyond Earth, enhancing our understanding of the universe and the various forms that life may take. The search for biosignatures combines multiple scientific disciplines, emphasizing the importance of collaboration in unraveling the mysteries of life in the cosmos. Life's potential for adaptation in environments radically different from Earth is a fascinating aspect of astrobiology, the study of potential life in the universe. Given the adaptability observed in extremophiles, organisms that thrive under extreme conditions on Earth, scientists speculate on a variety of ways that life could evolve to survive in diverse and harsh environments beyond our planet. One significant factor in adaptation is the biochemical makeup of organisms. While Earth-based life relies primarily on carbon, water, and amino acids, life in alternative environments might utilize different elements or solvents. For instance, scientists theorize that silicon could serve as a basis for life in environments where carbon is less abundant. Additionally, In places with limited liquid water, such as icy moons or planets, life may find options in other solvents like ammonia or methane, creating a fundamentally different biochemistry that still allows for cellular processes. Organisms may also develop unique physical characteristics to cope with extreme conditions. For instance, in very high-temperature environments, such as those found near hydrothermal vents, hypothetical life forms might evolve specialized heat-resistant proteins or membranes that maintain stability and function under intense heat. Conversely, in extremely low temperatures, organisms could develop anti-freeze-like compounds to facilitate metabolic processes. Adaptations to extreme pressure and radiation are also conceivable. On gas giants or planets with very high atmospheric pressures, life may evolve protective structures that can withstand such intense forces. Similarly, in environments with high radiation levels, organisms might have robust DNA repair mechanisms or build protective biofilms to shield themselves from damaging radiation. The ecological dynamics of life in radically different environments would also play a crucial role in adaptation. In the absence of sunlight, life forms might rely on chemosynthesis, deriving energy from chemical reactions rather than photosynthesis. This adaptation is already seen in Earth's deep-sea ecosystems, where organisms survive by metabolizing chemicals released from geological processes. The potential for life to adapt to extreme environments invites contemplation about the diversity of life forms we may encounter beyond Earth. As scientists investigate a range of celestial bodies such as Mars, Europa, and Titan, they consider the various conditions that could potentially foster life. By exploring the adaptability of life, they not only deepen our understanding of the resilience of life on Earth, but also expand the possibility of finding life forms that thrive in the vast and varied landscapes of the cosmos. Detecting and studying rogue planets, those that drift through space unbound to any star, presents unique challenges for astronomers. Despite these challenges, advances in technology and observational techniques have opened avenues for identifying these elusive worlds and learning more about their characteristics. One of the primary methods for detecting rogue planets is through gravitational microlensing. This phenomenon occurs when a rogue planet passes in front of a more distant star, temporarily magnifying the star's light due to the gravitational field of the planet. By measuring the light curve of the distant star, astronomers can detect the telltale signals of the planet's passing. This method has been successfully utilized in surveys like the Microlensing Observations in Astrophysics project, which has found evidence of several rogue planets in our galaxy. Another approach to identifying rogue planets involves infrared observations. Rogue planets do not produce their own light, making them difficult to detect in visible wavelengths. However, they can still emit thermal radiation, particularly if they are relatively warm or have undergone recent geological activity. Observatories equipped with infrared telescopes, such as the James Webb Space Telescope, can analyze the heat signatures of rogue planets as they drift through space. This allows astronomers to determine their temperatures, atmospheric compositions, and even potential surface conditions. Direct imaging is also a potential method for studying rogue planets, particularly if they are relatively nearby. Advanced imaging techniques, such as adaptive optics, allow telescopes to reduce the blurring of Earth's atmosphere and potentially capture images of these distant worlds. While this technique has had limited success so far, it offers a promising avenue for the future as technology improves. Once rogue planets are detected, studying their characteristics often involves analyzing their atmospheres and surface features using spectroscopy. By examining the light that passes through or reflects off a planet's atmosphere, scientists can identify the chemical signatures present, helping to determine the planet's composition, temperature, and potential for hosting life. The study of rogue planets enriches our understanding of planetary formation and evolution. Many of these planets are believed to have formed within their own solar systems before being ejected due to gravitational interactions, thus offering insights into the dynamics of planetary systems. As research progresses, the detection and analysis of rogue planets will continue to expand our knowledge of the vast and varied environments in our galaxy. Exploring the atmospheres of gas giants such as Jupiter and Saturn requires advanced technologies that can withstand harsh conditions and gather detailed scientific data. Several key types of technology and instrumentation play crucial roles in this endeavor. First, robust spacecraft designed for long-duration missions are essential. These spacecraft must be equipped to endure the extreme temperatures, radiation, and gravitational forces present in the environments of gas giants. For example, the Juno spacecraft, launched in 2016 to study Jupiter, utilizes a combination of advanced shielding materials and instrumentation to protect its systems from the intense radiation surrounding the planet. Such engineering innovations are critical for ensuring the longevity and functionality of the mission. Instruments for remote sensing are vital for analyzing the atmospheres of gas giants from a distance. Spectrometers, which measure the wavelengths of light emitted or reflected by atmospheric components, can provide detailed information about the chemical composition and structure of the atmosphere. These instruments can identify specific gases and their concentrations, offering insights into atmospheric processes, cloud formation, and potential weather patterns. Additionally, radar and microwave instruments have been employed to probe the deeper regions of gas giant atmospheres. These tools can penetrate thick layers of clouds, providing information on atmospheric dynamics and temperature profiles. For instance, Juno's microwave radiometer has been instrumental in revealing the structure of Jupiter's atmosphere beneath its cloud tops, offering clues about its atmospheric circulation and dynamics. Entry probes have also been proposed as a promising technology for future missions to gas giants. These robotic probes could be designed to descend through the atmosphere and collect data at various altitudes, directly measuring temperature, pressure, winds, and chemical composition in situ. This approach would provide invaluable details about the lower layers of a gas giant's atmosphere, enabling a more comprehensive understanding of its properties. Finally, satellite communications and data collection technologies play a critical role in transmitting the vast amounts of data gathered by these instruments back to Earth. Efficient communication systems are necessary to relay findings from the spacecraft to researchers, facilitating analysis and further exploration. The exploration of gas giant atmospheres represents a multifaceted technological challenge that combines robust spacecraft design, sophisticated instrumentation, and efficient data processing. As our understanding of these distant worlds expands, the development of new technologies will continue to enhance our ability to study gas giants, revealing the complexities of their atmospheres and offering clues about their formation and evolution within our solar system. Studying the interiors of icy moons like Europa and Enceladus is a compelling endeavor for planetary scientists, particularly due to the potential for harboring extraterrestrial life in their subsurface oceans. To explore these intriguing environments, scientists employ a combination of remote sensing, lander missions, and advanced modeling techniques to gain insights into their internal structures and dynamics. One primary method is remote sensing, where spacecraft equipped with sophisticated instruments analyze the surfaces and atmospheres of these moons from orbit. For instance, the Galileo spacecraft studied Europa in the late 1990s and revealed crucial surface features indicative of a subsurface ocean, such as ridges and cracks in the ice. Instruments like ice-penetrating radar can help determine the thickness of the ice shell covering the ocean, providing essential data on the size and depth of the ocean beneath. Another important technique involves measuring gravitational fields. As a spacecraft orbits a moon, its gravitational pull affects the trajectory of the spacecraft. By analyzing changes in the spacecraft's orbit, scientists can infer details about the moon's internal structure, such as variations in density and the presence of liquid water. This method has been successfully employed in prior missions and can help map out subsurface oceans and icy layers. Lander missions and in situ exploration also hold great promise for studying icy moons. While Europa and Enceladus have not yet hosted dedicated landers, future missions aim to send robotic landers or probes to these surfaces. Such missions could deploy instruments designed to directly sample the ice and any ejected plumes, particularly in the case of Enceladus, where geysers have been observed spraying water vapor and organic molecules into space. Analyzing these samples could reveal critical information about the Moon's subsurface ocean and its potential for supporting life. Models that simulate the conditions within these moons are also crucial for interpreting data and predicting how their interiors may operate. By combining observational data with advanced computer simulations, scientists can better understand the thermal evolution, ice dynamics, and potential chemical environments beneath the surface. The pursuit of knowledge about the interiors of icy moons like Europa and Enceladus is an exciting intersection of engineering, observational science, and astrobiology. As missions like NASA's Europa Clipper and ESA's Jupiter Icy Moons Explorer prepare to launch in the coming years, we are poised to uncover more about these enigmatic worlds and their potential to host the building blocks of life. Sending probes to nearby stars is an incredibly ambitious goal that poses several significant challenges, encompassing technological, financial, and logistical aspects. While the concept of interstellar travel has captivated the imagination of scientists and the public alike, the practicalities involved in such missions present formidable obstacles. One of the primary challenges is the immense distances involved. The closest star system, Alpha Centauri, lies approximately 4.3 light-years away from Earth. Even traveling at the speed of light, which is currently beyond our technological capabilities, it would take over 4 years to reach it. Current spacecraft travel at much slower speeds. For example, the Parker Solar Probe, one of the fastest human-made objects, can reach speeds of approximately 63 miles per second. At this pace, a journey to Alpha Centauri would take tens of thousands of years, making traditional means of propulsion impractical for interstellar missions. Developing propulsion systems capable of achieving a significant fraction of the speed of light is essential for making interstellar travel feasible. Concepts like solar sails, nuclear propulsion, and theoretical technologies such as antimatter engines or fusion drives are areas of active research. However, these advanced propulsion systems remain largely experimental, and significant engineering advancements are required to make them operational for crewed or uncrewed missions. Another obstacle is the communication delay that would come with interstellar missions. Once a probe is launched, it would take years for signals to reach Earth, hampering our ability to receive real-time data or give instructions to the spacecraft. This delay imposes limitations on remote operations and necessitates robust autonomous systems aboard the probe to conduct experiments and make decisions. Additionally, the harsh environment of space presents challenges for mission longevity. Probes would have to endure extended periods of radiation, extreme temperatures, and micrometeoroid impacts while traveling over vast distances. Developing durable instruments and systems capable of functioning reliably over many years or even decades is crucial to ensuring data collection and transmission after reaching a nearby star system. Finally, the financial implications of such missions are substantial. Funding interstellar probes would require significant investment from government agencies or private entities, which may prioritize other space exploration initiatives. The high cost, combined with the long timelines necessary for such projects, makes it challenging to secure ongoing support. While technological advancements and scientific creativity are making interstellar exploration more conceivable, significant challenges remain before we can successfully send probes to nearby stars. However, investigating these challenges can lead to innovations that also enhance our understanding of our own solar system, ultimately pushing the boundaries of human exploration beyond our cosmic neighborhood. Detecting and studying primordial black holes is a complex challenge that requires innovative approaches due to their unique origins and potential characteristics. Unlike stellar black holes, which form from collapsing massive stars, primordial black holes are theorized to have formed in the early universe, shortly after the Big Bang, due to density fluctuations in the rapidly expanding universe. Their size can vary widely, from very small to potentially large, depending on the conditions during their formation. One of the main methods for detecting primordial black holes involves searching for their gravitational effects on nearby objects. Primordial black holes, especially those with smaller masses, may go unnoticed because they do not emit light or radiation like other celestial objects. However, their presence can be inferred by observing gravitational lensing, a phenomenon where the gravity of the black hole bends the light from a background star. By analyzing distortions in the light patterns caused by gravitational lensing, astronomers can estimate the mass and location of primordial black holes. Whoa. Another observational signature of primordial black holes could be their impact on the cosmic microwave background radiation. If primordial black holes exist, they could contribute to the large-scale structure of the universe and influence the distribution of matter. Variations in the CMB could provide indirect evidence of their presence. Researchers use detailed maps of the CMB created by missions such as the Planck satellite to search for anomalies that might suggest the influence of primordial black holes on cosmic evolution. Primordial black holes may also produce gravitational waves when they merge with other black holes or compact objects. The advanced LIGO and Virgo observatories are designed to detect gravitational waves, and potential signals from merging primordial black holes could provide further insights into their properties. By analyzing these waveforms, scientists can glean information regarding the masses and distances of the black holes involved in these mergers. Moreover, if primordial black holes exist with smaller masses, they could also interact with dark matter in ways that lead to observable phenomena. Therefore, studying the nature of dark matter may provide indirect clues about the existence and characteristics of primordial black holes. While the quest to detect and study primordial black holes presents significant challenges, ongoing research and advancements in observational technologies and techniques continue to push the boundaries of astrophysics. As new telescopes, gravitational wave detectors, and cosmic surveys come online, the possibility of uncovering evidence of primordial black holes and learning more about their role in the evolution of the universe remains an exciting area of scientific inquiry. Exploring the galactic core, which is the central region of our galaxy, the Milky Way, presents a unique set of challenges. This area is characterized by high densities of stars, gas, and dust, along with intense gravitational forces and cosmic radiation. Nevertheless, advancements in technology and various observational methods provide pathways to study this enigmatic region more effectively. One of the primary methods for exploring the galactic core is through radio astronomy. Radio telescopes can penetrate the dense clouds of gas and dust that obscure visible light, allowing researchers to observe non-visible emissions from the core. By mapping the radio frequency signals emitted by various astronomical phenomena, such as supernovae remnants, pulsars, and the supermassive black hole known as Sagittarius A star, astronomers can gather valuable insights about the core's composition and dynamics. Infrared observations are another crucial tool for studying the galactic center. Infrared wavelengths can also penetrate dense dust clouds, which often obscure optical observations. Space-based observatories such as the Hubble Space Telescope and the upcoming James Webb Space Telescope are equipped with instruments that can operate in the infrared spectrum, allowing scientists to gather data on the stellar populations, gas dynamics, and the presence of forming stars in the core region. X-ray and gamma-ray astronomy provide additional complementary information about the galactic core. Observatories like the Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope can detect high-energy emissions from X-ray binaries, supermassive black holes, and gamma-ray bursts that are commonly found in the dynamic environment of the galactic center. These emissions can shed light on the energetic processes occurring there and help characterize the state of matter in extreme conditions. gravitational wave astronomy is also emerging as a potential method for exploring the galactic core. The merger of compact objects such as black holes and neutron stars can generate gravitational waves that propagate through the galaxy. By detecting and analyzing these gravitational waves with observatories like LIGO and Virgo, researchers can gain insights into the underlying mass distributions and dynamics of the core. Simulations and computational modeling play an essential role in theoretical studies of the galactic core. By creating computer simulations that replicate the complex interactions of stars, gas, and a supermassive black hole, scientists can test their hypotheses and gain a deeper understanding of the processes shaping the dynamics of this region. While exploring the galactic core poses significant challenges due to high density and radiation levels, the combination of radio, infrared, X-ray, and gravitational wave observations, along with theoretical modeling, provides powerful tools for investigating this complex environment. As technology continues to advance, our ability to study the galactic core will improve, offering profound insights into the nature of our galaxy and the fundamental processes that govern its evolution. Improving our ability to detect Earth-like exoplanets requires a combination of advanced technologies, innovative observational techniques, and comprehensive data analysis. Scientists and engineers are continually developing tools and methods to enhance the sensitivity and precision of exoplanet detection, particularly in searching for worlds that could support life. One of the most promising approaches is the deployment of next-generation space telescopes. The James Webb Space Telescope, which has recently launched, is poised to revolutionize our understanding of exoplanets by providing high-resolution infrared imaging and spectroscopy. These capabilities enable scientists to analyze the atmospheres of exoplanets, looking for chemical signatures that could indicate habitability or the presence of life. Future missions, such as the ESA's Ariel and NASA's LUVOIR or HABEX, aim to further refine the search for Earth-like planets around Sun-like stars using advanced techniques. The transit method remains one of the most effective techniques for detecting exoplanets. Observing the periodic dimming of a star's light as a planet passes in front of it enables researchers to infer the planet's size, orbit, and distance from the star. To improve sensitivity, larger and more powerful telescopes equipped with precise photometers are being developed to detect smaller transiting planets, enhancing the chances of discovering Earth-like exoplanets in the habitable zone around their stars. Another key technology is the use of direct imaging techniques, which can help identify exoplanets by blocking out the light from their host stars. Adaptive optic systems and coronagraphs are instrumental in enhancing image quality and enabling the detection of faint planets close to bright stars. Continued advancements in these techniques could improve our ability to find and characterize nearby Earth-like exoplanets. Radial velocity measurements remain vital for detecting exoplanets as well. This method involves measuring the wobble of a star caused by the gravitational influence of an orbiting planet. Enhanced spectrographs and high-precision instruments increase the sensitivity of radial velocity measurements, allowing astronomers to detect smaller, Earth-sized planets around distant stars. Finally, utilizing machine learning and artificial intelligence can significantly enhance data analysis. These technologies can sift through vast amounts of observational data, detecting patterns and identifying potential exoplanet candidates more efficiently than traditional methods. By automating parts of the analysis process, machine learning algorithms can streamline the detection process, making it easier to find Earth-like exoplanets hidden among other signals. By integrating these advanced technologies, improving observational strategies, and expanding our analytical capabilities, the search for Earth-like exoplanets can become increasingly effective. The ongoing quest to detect and characterize these distant worlds holds the potential to answer fundamental questions about life's existence beyond our planet and the conditions necessary for habitability in the universe. Harnessing antimatter for space propulsion presents a tantalizing prospect for the future of space exploration, offering the potential for incredibly efficient propulsion systems. Antimatter, the counterpart to ordinary matter, annihilates upon contact with its matter equivalent, releasing vast amounts of energy according to the principles of Einstein's mass-energy equivalence. This annihilation reaction produces energy with a specific energy yield far greater than that of conventional chemical propellants, making antimatter a compelling candidate for advanced propulsion technologies. One of the primary advantages of antimatter propulsion is the potential for high thrust-to-weight ratios. This capability would enable spacecraft to achieve much higher speeds than are possible with current propulsion methods, allowing for faster travel to distant destinations within our solar system and even beyond. Theoretically, a spacecraft powered by antimatter engines could reach a significant fraction of the speed of light, significantly reducing travel times to nearby stars and increasing the feasibility of interstellar exploration. However, several significant challenges must be addressed before antimatter can be harnessed for practical propulsion. The production of antimatter is currently highly inefficient and expensive. Antimatter is generated in particle accelerators such as CERN, but the quantities produced are minuscule. Current estimates suggest that producing even a gram of antimatter could cost trillions of dollars, making it economically impractical at present. Developing methods for mass production of antimatter or finding more cost-effective means to create or capture antimatter is essential if we wish to utilize it as a propulsion system. In addition to production challenges, safely storing and handling antimatter is critical. Antimatter must be kept in a vacuum with magnetic or electromagnetic fields to prevent it from coming into contact with matter, as any interaction would result in annihilation and release enormous amounts of energy. Designing safe containment systems that can effectively maintain antimatter for long durations remains a considerable engineering challenge. There is also the need for appropriate mission design that maximizes the advantages of antimatter propulsion while minimizing risks. This would involve careful planning regarding trajectories, potential uses in deep space exploration, and integrating the technology with existing spacecraft systems. As research in antimatter physics advances, the exploration of antimatter propulsion will continue to be a topic of intense interest. While fully realizing the potential of antimatter propulsion may still be far in the future, continued investment in fundamental research, production technologies, and engineering solutions could gradually bridge the gap between theoretical possibilities and practical applications. This pursuit not only expands our understanding of fundamental physics, but also opens exciting avenues for the future of human exploration beyond our solar system. If a magnetar, a highly magnetized and rapidly rotating neutron star, were to come close to our solar system, the consequences could be significant and potentially catastrophic. Magnetars are known for their extraordinarily strong magnetic fields, which can be more than 1,000 times stronger than those of typical neutron stars and trillions of times stronger than the Earth's magnetic field. These intense magnetic fields, combined with the high-energy emissions from a magnetar's surface, could pose serious threats to our planet. One of the most immediate effects would be the impact of the magnetar's magnetic field on Earth. A magnetar passing within a few light years could distort and disrupt the Earth's own magnetic field, potentially leading to geomagnetic storms. These storms could affect power grids and satellite communications, causing broad disruptions to technological systems. In extreme cases, the induced electrical currents could even damage transformers and other critical infrastructure, leading to blackouts and long-term electrical outages. The high-energy emissions from a magnetar, particularly in the form of X-rays and gamma rays, could have severe biological consequences. A magnetar emits bursts of high-energy radiation, which are some of the most powerful observed in the universe. If a magnetar were to come within a range of just a few hundred light-years, the resultant emission could bombard the Earth with harmful radiation. Such an event could lead to increased rates of cancer and other health issues, especially in those exposed to elevated radiation levels. Additionally, the intense radiation could have detrimental effects on Earth's atmosphere. High-energy gamma rays could lead to increased ionization in the atmosphere, potentially depleting the ozone layer. A compromised ozone layer would allow more ultraviolet radiation to reach the surface, affecting both ecosystems and human health. The gravitational influence of a magnetar would also be a factor to consider. While a magnetar is extremely dense, an encounter close enough to affect our solar system's gravitational dynamics could perturb the orbits of planets, comets, and asteroids, leading to possible changes in their trajectories and interactions. However, such dramatic gravitational effects would generally require the magnetar to be incredibly close, on the order of a few astronomical units, which is an unlikely scenario. Overall, while the likelihood of a magnetar coming close enough to our solar system to cause significant effects is extremely low, the potential consequences would be profound. Understanding these interactions and their risks provides valuable insights into cosmic events and underscores the delicate balance of conditions that support life on Earth. Take C. Gamma-ray bursts are among the most energetic and destructive phenomena observed in the universe, often associated with the death of massive stars or the merging of neutron stars. When these bursts occur, they release enormous amounts of gamma radiation, which can have profound effects on their host galaxies and the potential for life within them. One of the most immediate and severe impacts of a gamma-ray burst is the intense radiation it emits. If such a burst is directed towards a planet, the high-energy gamma rays can penetrate atmospheres and cause significant biological damage. This radiation can lead to increased ionization of atmospheric particles, potentially creating conditions similar to those caused by a massive solar flare, but on a far more catastrophic scale. The resulting increase in radiation can disrupt cellular processes, leading to increased mutation rates and a higher likelihood of cancer and other health issues for any life forms that might be exposed. In addition to the direct biological effects, it could potentially have grave implications for any life in that region of space. However, bursts occurring at much greater distances would likely have reduced effects due to the dispersion of energy over vast distances. Interestingly, some scientists propose that gamma-ray bursts might also influence the process of star formation within their host galaxies. The intense shock waves produced by the explosion can compress nearby gas and dust, potentially triggering the formation of new stars and possibly even new planetary systems. While this could lead to the emergence of new environments where life might arise, the initial immediate impact would likely be destructive rather than constructive. Given the rarity of gamma-ray bursts and their specific conditions of occurrence, it is believed that life on Earth has not been significantly affected by them. However, the implications of such events raise important questions about the habitability of other star systems throughout the universe. Understanding how gamma-ray bursts interact with their environments expands our knowledge of cosmic events that shape the conditions under which life might develop and thrive. Galactic collisions, or the merging of two galaxies, are monumental events in the cosmic timeline that can significantly reshape star systems over long timescales. As galaxies collide and interact, the gravitational forces at play lead to a range of effects, influencing star formation, stellar dynamics, and the overall structure of the merging galaxies. One of the most profound long-term effects of galactic collisions is the enhancement of star formation rates. When galaxies collide, their gravitational interactions can compress gas and dust within them, triggering a phenomenon known as starburst. This compression increases the density of star-forming regions, leading to rapid star formation. In some cases, new stars are born at rates several times greater than in non-interacting galaxies. This burst of activity can populate the galaxies with new stars, including massive stars that may eventually end their lives in supernova events. The dynamics of existing star systems can also experience substantial changes during and after a galactic collision. As the gravitational forces exerted by the incoming galaxy influence the orbits of stars and gas clouds, many star systems may be perturbed from their original orbits. Some stars might be ejected from their host galaxies entirely, becoming free-floating stars in intergalactic space. Others may be drawn into denser regions and participate in the formation of new stellar clusters or even merge with other stars, leading to binary or multiple star systems. Galactic mergers often result in the formation of new structures within the resulting galaxy. For example, the interaction between two spiral galaxies may create a more elliptical galaxy post-collision, and spiral arms may be distorted or diminished. The redistribution of stars and gas can lead to new dynamics and evolution of the overall galactic structure. Additionally, the merger of galaxies can influence the supermassive black holes at their centers. During a collision, the black holes may eventually find themselves closer together, leading to interactions that can result in the formation of binary black holes. Over time, the gravitational waves emitted by these merging black holes can even offer insights into the history of the merging galaxies. Over long timescales, the effects of galactic collisions can also alter the habitability of star systems. For instance, increased stellar activity and the resulting radiation from starburst periods may influence the atmospheres and conditions on surrounding planets. This dynamic environment can either promote or inhibit the potential development of life. Long-term effects of galactic collisions on star systems encompass a spectrum of processes that lead to enhanced star formation, alterations in stellar dynamics, and the transformation of galaxy structures. As galaxies collide, they create complex and evolving environments that shape the future of both existing stars and potential planetary systems. Exploring these phenomena deepens our understanding of cosmic evolution and the driving forces behind the formation of the structures we observe in the universe today. Supernova explosions, the dramatic deaths of massive stars, release an immense amount of energy and are among the most energetic events in the universe. While they can be devastating to their immediate surroundings, planetary systems can survive these cataclysmic events under certain conditions, primarily depending on their distance from the explosion and the dynamics involved in the supernova itself. The influence of a supernova on nearby planetary systems is significant in terms of radiation and shock waves. When a star goes supernova, it emits a powerful burst of radiation, including intense gamma rays and X-rays, which can disrupt the atmospheres of surrounding planets. However, if a planetary system is located far enough away from the supernova, the effects may be minimal. For instance, studies suggest that a safe distance for planetary systems to avoid catastrophic damage is generally tens of light years away from the supernova explosion. At this distance, the radiation's impact diminishes significantly, allowing planets to retain their atmospheres and potentially their capacity for habitability. The shockwave generated by a supernova can also have various effects on a planetary system. This shockwave travels outward and can compress surrounding interstellar gas and dust, triggering star formation in nearby molecular clouds. For planetary systems situated further from the supernova, this interaction may lead to an influx of material that could enhance the potential for new planet formation or contribute to the existing protoplanetary disks. Even for those planetary systems closer to the supernova, there is a potential for survival. If the explosion occurs in a binary star system, the dynamics of the surviving companion star may stabilize remnants of the planetary system. In cases where an existing planet orbits a massive star that goes supernova, it may continue orbiting the remnant neutron star or black hole. Such remnants can retain significant gravitational influence over the surrounding planets. In some scenarios, the supernova can enrich the interstellar medium with elements heavier than helium, known as metals. This enrichment can enhance the material available for the formation of new stars and planets in the future, thereby contributing to the galaxy's evolution and promoting the development of new planetary systems. Ultimately, the survival of planetary systems following a supernova explosion is contextual and heavily dependent on specific conditions, including the initial distance from the explosion, the nature of the surrounding environment, and the evolutionary history of the host star and its companions. As scientists explore the life cycles of stars and their potential to facilitate or hinder planetary formation, understanding these dynamics sheds light on the broader processes driving the evolution of galaxies and the potential for life throughout the cosmos. A hypernova, an exceptionally energetic supernova associated with the collapse of a massive star, releases an enormous amount of energy, up to 100 times more than a typical supernova. If a hypernova were to occur relatively close to Earth, within a range of several tens of light years, the consequences could be profound and potentially catastrophic for our planet and the surrounding solar system. One of the most immediate effects of a nearby hypernova would be the intense burst of radiation it emits, particularly in the form of gamma rays. If directed toward Earth, this radiation could pose a significant threat to the atmosphere and life on our planet. The gamma rays would increase ionization in the atmosphere, leading to the depletion of the ozone layer. A compromised ozone layer would allow higher levels of ultraviolet radiation from the sun to reach the surface, which can cause severe harm to biological systems, including increased rates of skin cancer, harm to plant life, and the disruption of ecosystems. In addition to radiation effects, the shock wave generated by a hypernova would travel through space at high speeds, compressing interstellar gas and dust in its path. This shock wave could also impact the Earth's atmosphere, potentially triggering severe weather phenomena and accelerating the dynamics of the atmosphere. While the most immediate impact from the shock wave would likely be felt at the cosmic scale, it could also lead to disturbances in Earth's geological and atmospheric conditions. Furthermore, if the hypernova occurs close enough, it could result in an influx of cosmic rays and high-energy particles bombarding the solar system. This would increase the levels of radiation that reaches Earth, which might affect satellites, disrupt technology, and pose risks to human health, particularly for those in high-altitude flights or space missions, as they would experience elevated radiation levels. The long-term consequences could also be significant. The energetic output of a hypernova contributes to the enrichment of the interstellar medium with heavy elements, such as iron and nickel, allowing for the potential formation of new stars and planetary systems. While this process can enhance future star formation in the galaxy, the immediate threats from the hypernova would overshadow such effects for existing life forms. Interestingly, there is also the question of how a hypernova would affect nearby star systems. Stellar dynamics may shift as the hypernova disperses material and alters gravitational influences in the region. Planets in nearby systems could experience perturbations in their orbits, potentially leading to destabilization. A nearby hypernova could present a multifaceted threat to Earth and its inhabitants, primarily through intense radiation, atmospheric disruption, and increased cosmic radiation exposure. While the probability of such an event occurring in proximity to our solar system is low, understanding the dynamics and implications of hypernovae enhances our knowledge of cosmic events and their potential impacts on planetary systems and life as we know it. Massive solar flares, sudden bursts of radiation and energy from the sun's surface, have significant impacts on space weather and can affect planetary atmospheres in various ways. Understanding these effects is crucial for protecting satellites, astronauts, and ground-based technologies from the potentially damaging consequences of heightened solar activity. When a solar flare occurs, it releases a burst of electromagnetic radiation across the entire electromagnetic spectrum, including visible light, ultraviolet light, X-rays, and gamma rays. As part of this release, energetic particles are also accelerated, creating a storm of high-energy solar particles that travel outward from the sun. When these particles reach Earth, they can interact with the planet's magnetic field, leading to phenomena such as geomagnetic storms and auroras. The immediate impacts on Earth's atmosphere can manifest through this interaction with the magnetosphere. Geomagnetic storms driven by the influx of energetic particles from flares and associated coronal mass ejections can disturb the Earth's magnetic field, inducing currents in the ionosphere. These disturbances can disrupt radio communications, satellite operations, and navigation systems, posing risks to technology based on electromagnetic signals. For planets with substantial atmospheres, massive solar flares can also lead to significant alterations in atmospheric composition. The increased levels of ultraviolet radiation and energetic particles can enhance chemical reactions within the atmosphere, sometimes resulting in the production of nitric oxide and other compounds that can deplete the ozone layer. A weakened ozone layer can allow even more harmful ultraviolet radiation to penetrate the atmosphere, affecting both surface conditions and potential life forms. For planets with thinner or less protective atmospheres like Mars, the situation can be even more severe. While Earth's magnetic field provides a shield against solar wind and radiation, Mars lacks a global magnetic field, making it more vulnerable. Solar flares and the resulting enhanced solar wind can strip away the Martian atmosphere over time, contributing to its present-day thin atmosphere and affecting any potential for sustaining life. Additionally, massive solar flares can have a more immediate impact on space missions. Astronauts and equipment in space must be protected from the intense radiation that accompanies large flares, which can increase the risk of acute radiation exposure. Space agencies monitor solar activity closely to ensure the safety of crewed missions and to prepare satellites for potential disruptions. Massive solar flares significantly influence space weather by releasing a burst of energy and charged particles that interact with planetary atmospheres. The effects range from disruptions in communications and satellite operations on Earth to potential atmospheric changes and erosion on planets like Mars. Monitoring solar activity and understanding its implications for space weather is essential for safeguarding technology and exploring the far reaches of our solar system.